On the evening of August 15th, 1977, a radio astronomer named Jerry Amon was sitting in front of a computer printout at Ohio State University's Big Ear Radio Telescope, scanning the heavens for any signs of extraterrestrial intelligence as part of the ongoing SETI program, when he noticed something extraordinary that would perplex the scientific community for decades to come. The telescope had detected an unusually strong and narrowband radio signal originating from a position in the constellation Chi Sagittarii, a signal so remarkable and so anomalous that Amon immediately circled it on the printout and wrote the word "wow" in the margin beside the data, a response that perfectly captured the astonishment and bewilderment he felt in that singular moment. The signal bore all the hallmarks of what scientists had theorized an extraterrestrial transmission might look like. It was narrowband, meaning it occupied only a tiny sliver of the radio spectrum, far narrower than anything natural astronomical objects typically produce, and it appeared to come from a point source rather than being spread across the sky, characteristics that seemed to rule out conventional explanations like terrestrial radio interference or natural cosmic phenomena. The signal persisted for exactly 72 seconds before vanishing entirely, leaving behind only that cryptic notation on the paper and a mystery that would captivate astronomers, physicists, and the general public for nearly 50 years. Despite intensive follow-up observations conducted immediately afterward and in the decades since, using increasingly sophisticated radio telescopes and detection equipment, the signal has never been observed again, and the original source has never been definitively identified, creating a peculiar psychological phenomenon wherein the absence of explanation becomes its own form of explanation. What makes the WOW signal so psychologically compelling is the profound human tendency to interpret ambiguous data through the lens of our deepest hopes and fears, allowing a momentary anomaly detected once and never replicated to become transformed into something far larger in our collective imagination, a potential proof of life beyond Earth that simultaneously validates our cosmic significance and terrifies us with the implications of contact. Yet the very characteristics that made the signal so tantalizing have been systematically analyzed and challenged by subsequent researchers who have proposed mundane alternatives. A reflected satellite signal, terrestrial interference miscategorized, or some yet unknown natural phenomenon we have not encountered before. The WOW signal persists in popular culture and scientific discourse not because of any new evidence or repeated observations, but because the human mind finds a beautiful and deeply satisfying narrative in an eternal unsolved mystery, something that defies complete rational explanation and reminds us that our understanding of the universe remains fundamentally incomplete and perpetually humbled by the vastness of space and the limits of our detection capabilities. Imagine standing at the edge of the observable universe, looking outward in all directions and discovering that everything around you is moving in a direction you cannot explain. This is the essence of dark flow, a cosmological anomaly that has puzzled astronomers and physicists for nearly 2 decades. In the early 2000s, researchers analyzing the motion of galaxy clusters noticed something extraordinary. These massive structures, which should be distributed randomly throughout space according to our understanding of cosmic expansion, appeared to be moving together toward a particular region of space with a velocity of several hundred kilometers per second. This movement was not caused by the gravitational attraction of nearby matter, nor could it be accounted for by the known forces shaping the universe. The phenomenon seemed to suggest that galaxies and clusters were being pulled or pushed by something lurking beyond the observable cosmic horizon, some massive gravitational structure so distant and so vast that we cannot see it directly, yet its influence reaches across billions of light years to affect the motion of matter within our own cosmic neighborhood. The psychological mechanism at work here involves our deep human need to maintain a coherent, comprehensible universe, and dark flow challenges this need fundamentally by suggesting that our cosmic understanding might be incomplete in ways we cannot yet measure or verify. Scientists initially accepted dark flow as a genuine anomaly requiring serious investigation, yet subsequent observations and refined analyses have suggested that the effect may be weaker than originally proposed, possibly even attributable to statistical fluctuations or systematic errors in measurement techniques. What persists despite this uncertainty is a haunting recognition that the universe may contain structures and influences operating beyond our current observational capabilities, forces that shape cosmic evolution in ways we have yet to fully comprehend, leaving us with the unsettling awareness that our position within the cosmos may be more peripheral and mysterious than we have long assumed. The search for dark flow has led researchers to examine whether equally mysterious phenomena, such as the axis of evil, an unexpected alignment in the cosmic microwave background, or the Great Attractor, a gravitational anomaly pulling galaxies toward the Coma cluster, might be interconnected pieces of a larger cosmic puzzle we are only beginning to perceive. In this sense, dark flow represents not merely an isolated curiosity, but a humbling reminder that the universe reserves its deepest secrets for those patient enough to question their assumptions about reality itself. And so, as telescopes grow more powerful and our measurements more precise, the question of dark flow endures, whether it represents a genuine cosmic phenomenon waiting to be explained or a mirage born from the limits of our instruments and methods, a distinction that may ultimately reveal as much about the nature of scientific inquiry itself as it does about the universe we seek to understand. Imagine standing in a vast, dark ocean where invisible currents pull everything toward a mysterious direction, a force so immense that entire galaxies spanning millions of light-years are being drawn toward it with inexorable gravitational power, and yet despite centuries of astronomical observation and sophisticated mathematical modeling, we cannot fully explain what creates this tremendous phenomenon or where it ultimately lays. This is the nature of the Great Attractor, a gravitational anomaly discovered in the 1970s when astronomers noticed that galaxies in our local universe appeared to be moving toward a specific region in space, not due to the expansion of the universe itself, but because of some massive concentration of matter exerting a pull across unfathomable distances. The gravitational effect is so powerful that it influences the motion of billions of galaxies, including our own Milky Way, bending their trajectories in ways that should not be possible if the visible matter we can observe is all that exists. When scientists examined this region more carefully, they discovered that the known galaxies and clusters visible in that direction simply did not possess enough mass to account for the gravitational force being observed, leading to the profound realization that most of what pulls on our galaxy remains completely invisible to us. We call this missing mass dark matter, a hypothetical substance that appears to make up the vast majority of the universe's gravitational influence, yet it leaves no light, emits no radiation, and interacts with ordinary matter only through gravity, making it fundamentally undetectable through conventional astronomical methods. The psychological impact of this discovery cannot be overstated, as it revealed that everything we can see and measure with our instruments represents only a small fraction of what actually exists, that we are essentially blind to the universe's true composition, and that powerful forces shape our cosmic neighborhood from the shadows in ways we cannot fully comprehend. Despite decades of research involving the most advanced telescopes and detection equipment ever constructed, the Great Attractor remains largely mysterious, resisting our attempts at complete explanation, and we have normalized this profound ignorance by accepting it as simply another feature of our expanding cosmic knowledge, rather than acknowledging the unsettling truth that massive portions of reality remain fundamentally beyond our capacity to perceive or understand. Existing just outside the boundaries of human sensory limitation and technological reach. Yet perhaps this cosmic humility serves a purpose, reminding us that the universe operates according to principles far grander than our current instruments can measure, and that the Great Attractor, whether it proves to be a concentration of dark matter, a gateway to another dimension, or something we have not yet conceived, stands as an eternal monument to the limits of human knowledge and the vast territories of wonder that still await our discovery. In the vast expanse of the observable universe, there exists a region of space so profoundly empty that it challenges our fundamental understanding of cosmic distribution and structure. A cosmic void located approximately 250 million light-years away from Earth in the direction of the constellation Boötes, and this void spans an almost incomprehensible distance of roughly 330 million light-years in diameter, making it one of the largest structures known to humanity. Within this enormous spherical region, galaxies are so sparsely distributed that the void contains far fewer galaxies than would be expected based on the statistical models that astronomers have developed over decades of observation. And this dramatic deficit of galactic matter stands in stark contrast to the dense filaments and clusters of galaxies that characterize other regions of the cosmic web. The Boötes void was first identified in the 1980s when astronomers conducting systematic surveys of galaxy distributions noticed a peculiar and unsettling emptiness, a region where the expected density of galaxies simply did not materialize, and subsequent observations using increasingly sophisticated telescopes confirmed that this void was indeed a genuine feature of the universe rather than a mere observational artifact or systematic error. The psychological and conceptual mechanism behind our fascination with this void stems from the fundamental human need to find patterns and structure in the cosmos. And when we encounter such a dramatic violation of those expected patterns, it creates a kind of cognitive dissonance that compels us to seek explanations and understanding. Yet despite decades of intense astronomical study and the development of sophisticated computer models attempting to explain how such voids form and persist, we remain largely uncertain about the precise mechanisms that created the Boötes void, or why it maintains such an extraordinarily low density of matter across such an immense volume of space. We have normalized this cosmic mystery by incorporating it into our standard models of universe formation and evolution, discussing it in textbooks and scientific papers as if we fully comprehend its significance. Yet the simple truth remains that the Boötes void represents a gap in our understanding of how the universe organizes itself on the largest scales. Perhaps this humbling realization, that we can measure the void's dimensions with precision yet remain mystified by its origin, serves as a potent reminder that the universe continues to conceal fundamental secrets, and that our maps of cosmic structure, however detailed, remain incomplete sketches of a reality far more complex than our current theories can fully encompass. The Boötes void thus stands alongside other cosmic mysteries, dark matter, dark energy, the universe's accelerating expansion, as a testament to the provisional nature of scientific knowledge, reminding us that observation and measurement, while essential tools, are merely the first steps toward genuine comprehension. When astronomers peer at the cosmic microwave background radiation, the ancient light that fills the entire universe with a nearly uniform glow of thermal energy from the Big Bang itself, they encounter something profoundly unexpected and deeply unsettling. A vast region of space, stretching across nearly 1% of the entire visible sky, where this radiation appears significantly colder than it should be. This anomaly, first detected in the year 2005 through careful analysis of satellite data, covers an area roughly equivalent to 15 full moons placed side by side, and it radiates at temperatures noticeably lower than the surrounding cosmic fabric, defying the theoretical predictions of our standard models of cosmology. Scientists have named this phenomenon the cold spot, and its existence has troubled the theoretical physics community for nearly 2 decades, because according to everything we understand about the universe's formation and structure, this region should not exist in any meaningful way. The prevailing theory suggests that the cosmic microwave background should display only tiny, random variations in temperature across the sky, patterns that arise naturally from quantum fluctuations during the universe's inflationary period. Yet the cold spot appears far too large, far too coherent, and far too cold to be explained by such conventional processes alone. Some researchers have proposed exotic explanations, including the possibility that a supermassive void in the universe, a region containing far fewer galaxies than normal, might bend light from distant regions and create the appearance of unusual cold, while other scientists have suggested even more speculative ideas, such as the collision of our universe with another parallel universe, or the presence of exotic structures in spacetime that we do not yet comprehend. Despite numerous investigations, improved satellite measurements, and increasingly sophisticated analytical techniques, the cold spot persists as an enigmatic feature of our cosmos, challenging our understanding of fundamental physics and reminding us that even after decades of careful observation and theoretical advancement, the universe continues to harbor secrets that seem to violate the very laws we have worked so carefully to establish. Leaving us suspended between the comfort of our established knowledge and the unsettling recognition that the universe may operate according to principles we have not yet discovered. Perhaps most humbling is the possibility that the cold spot may represent not a failure of our models, but rather evidence that we are only beginning to glimpse the true complexity of cosmic structure. A reminder that each answer we find in the universe often opens doors to questions we had never thought to ask, and that the pursuit of understanding the cosmos is ultimately a journey without final destination. In the distant reaches of the Cygnus constellation, approximately 430 light-years from Earth, there exists a star that has fundamentally challenged our understanding of stellar behavior and the known laws of physics in ways that continue to perplex astronomers and astrophysicists worldwide. This star, formally designated as KIC 8,462,852, but colloquially known as Tabby's star, named after the citizen scientist Tabitha Boötes, who first brought attention to its extraordinary characteristics, exhibits patterns of dimming that possess no conventional explanation within our current scientific framework. Unlike ordinary stars that maintain relatively constant brightness or experience predictable variations due to stellar rotation or the passage of distant planets across their surfaces, Tabby's star displays irregular, dramatic, and inexplicable fluctuations in luminosity that have led researchers to propose increasingly unconventional theories about what might be obscuring its light. When astronomers first analyzed data from the Kepler Space Telescope, they observed that this star's brightness would diminish by up to 22% over irregular intervals, with some dimming events lasting mere days while others persisted for weeks, and these variations showed no correlation to any known celestial mechanics. The initial hypothesis suggested that a swarm of comets might be orbiting the star in a chaotic configuration, occasionally passing between the star and our telescopes, yet this explanation fails to account for the asymmetry of the dimming patterns and the irregularity with which they occur. More radical theories have emerged, including speculative considerations of a Dyson sphere, a hypothetical megastructure that an advanced civilization might construct to harvest stellar energy, though such structures remain entirely in the realm of theoretical physics and pure conjecture. What makes Tabby's star particularly vexing to the scientific community is that despite decades of intensive observation and analysis using multiple telescopes and detection methods, no definitive answer has emerged, and the star continues to dim and brighten in ways that defy categorical explanation. The persistence of this mystery, even as it sits squarely within our technological reach and observation capabilities, represents a humbling reminder that the universe continues to harbor phenomena that slip through the nets of our most rigorous scientific models, defying our best efforts to categorize and understand it. Recent spectroscopic analyses have revealed unusual chemical signatures in the star's atmosphere, hinting at possible collisions between massive objects in its vicinity, while simultaneously, citizen scientists continue to monitor its behavior through crowdsourced observation networks, transforming Tabby's star into a global collaborative endeavor that exemplifies how the greatest scientific mysteries can unite researchers across institutional boundaries in pursuit of understanding. In the vastness of space, approximately 170 million light-years away, there exists a celestial structure so geometrically perfect and so utterly defiant of our understanding of galaxy formation that astronomers have struggled for decades to explain its very existence. And this remarkable object is known as Hoag's object, a galaxy that presents itself as a nearly perfect golden ring of stars surrounding an apparently empty core of darkness. A configuration so symmetrical and so aesthetically improbable that, when it was first observed by American astronomer Art Hoag in 1950, many scientists initially suspected it might be a photographic artifact or some peculiar optical illusion caused by the limitations of observation technology. The galaxy appears as a luminous circle, roughly 100,000 light-years in diameter, composed of brilliant blue and white stars that seem to orbit around a central void, while within that mysterious darkness lies only a thin scattering of yellowish stars that suggest an older stellar population, a composition that fundamentally contradicts everything we understand about how galaxies form and maintain their structure over billions of years. In our conventional models of galaxy evolution, we expect to see dense central bulges or supermassive black holes around which matter accumulates and organizes. We anticipate gradual density gradients, and we predict that gravitational forces should create asymmetrical distributions rather than these impossibly precise geometric arrangements. Yet Hoag's object persists in its perfection, rotating with such uniformity and such gravitational balance that it should not, by any reasonable measure of physics, actually exist in this configuration at all. Despite having no central anchor of significant stellar density to explain how such a perfect ring could form and maintain its coherence against the gravitational disruptions that permeate the cosmos, despite the complete absence of clear mechanisms that would create such astonishing symmetry, and despite the logical expectation that billions of years of cosmic interactions would have distorted or destroyed such a delicate arrangement. We continue to observe this galaxy in this exact same pristine state, as though some unknown force has designed and then perpetually balanced this structure in defiance of entropy and chaos, reminding us that our models of the universe, for all their mathematical sophistication, may still be missing something fundamental about how galaxies can organize themselves in the darkness between the stars. Perhaps most intriguingly, astronomers have discovered that Hoag's object is not alone. Other similar ring galaxies have been identified throughout the universe, suggesting that this geometric perfection may represent an entirely separate class of galactic structures awaiting explanation. Structures that challenge us to expand our theoretical frameworks and acknowledge that the cosmos still harbors mysteries profound enough to reshape our understanding of gravitational physics itself. Consider the sheer mathematical probability that we are not alone in this universe, a calculation that seems almost impossible to deny when we contemplate the truly staggering scale of cosmic existence. There are an estimated 2 trillion galaxies in the observable universe, and within each galaxy exist hundreds of billions of stars, many of which host planetary systems of their own, creating an incomprehensibly vast arena where life could potentially emerge and flourish across countless worlds. The laws of chemistry and physics that govern the formation of life on Earth are universal constants, operating identically throughout the cosmos, which logically suggests that given enough time and the right conditions, life should arise naturally on countless worlds throughout space. And yet, when we gaze up at the night sky with our most powerful telescopes and listen intently with our most sensitive radio equipment designed to detect signals from distant civilizations, we encounter only silence, an absolute and profound silence that seems to contradict everything our mathematics tells us should be true about the prevalence of life in the universe. This paradox, articulated by physicist Enrico Fermi in 1950, sits at the intersection of probability and observation, creating a tension that has troubled scientists and philosophers for decades. The mechanism behind this paradox emerges from the fundamental disconnect between two competing frameworks. The first suggests that given the age of the universe, roughly 13.8 billion years old, countless civilizations should have emerged long before humanity appeared on Earth, and many of these civilizations should have developed interstellar travel or communication technologies that would make their presence unmistakably evident to us. The second framework acknowledges that despite this logical imperative, we have found absolutely no credible evidence of any extraterrestrial civilization, no radio signals, no visits, no artifacts, no signs whatsoever of intelligent life beyond our small blue planet. Yet despite the logical force of this paradox, despite its fundamental challenge to our assumptions about life and intelligence in the universe, we continue to maintain a kind of comfortable cognitive distance from its implications, neither fully embracing the possibility of abundant alien civilizations nor seriously grappling with what their apparent absence might actually mean about existence itself. Perhaps this cognitive dissonance itself reveals something profound, that we are caught between the mathematical certainty of probability and the humbling silence of observation, forced to confront the possibility that either life is far rarer than we assume, or that civilizations inevitably destroy themselves before reaching for the stars, or that we are simply listening in the wrong way, at the wrong time, in the wrong part of the universe for signals that may have already passed us by. The great filter, as some theorists call it, may lie behind us in our own evolutionary past, or it may await us somewhere in our future, a cosmic hurdle so formidable that few civilizations survive to cross it and announce their presence to the cosmos. When astronomers observe the rotation of galaxies, they encounter a profound cosmic puzzle that has resisted explanation for decades, a mystery so fundamental that it challenges our understanding of gravity itself and forces us to reconsider what comprises the majority of the universe. As galaxies spin, the outer regions should fly apart due to insufficient gravitational force from the visible matter alone, yet they remain cohesive and stable, rotating as though held together by an invisible gravitational anchor that accounts for roughly 85% of all matter in existence. This unseen substance, which we call dark matter, cannot be detected through any form of electromagnetic radiation. It emits no light, absorbs no light, and reflects no light, making it entirely invisible to every telescope humanity has ever constructed, whether observing in visible wavelengths, infrared, ultraviolet, X-rays, or radio frequencies. The gravitational effects of dark matter are undeniable and measurable. We can observe its influence on the rotation curves of galaxies, on the motion of galaxy clusters, on the way light bends around massive objects through gravitational lensing, and on the temperature variations in the cosmic microwave background radiation that permeates all of space. Despite decades of intensive research and theoretical development, scientists have proposed numerous candidates for what dark matter might be, including exotic particles with names like weakly interacting massive particles, or WIMPs, and axions, theoretical particles that could be produced in enormous quantities in the early universe. Yet not a single particle of dark matter has ever been captured or directly detected in any laboratory experiment. The peculiar aspect of dark matter's persistence in scientific discourse lies in how the scientific community has normalized its existence without understanding its nature. We accept that 85% of matter in the universe is fundamentally unknown to us, yet we continue building our cosmological models upon this invisible foundation, treating dark matter not as a temporary placeholder, but as an established reality requiring explanation, rather than as a sign that our theories of gravity might require fundamental revision. Perhaps this acceptance reflects a deeper truth about scientific progress, that sometimes our most profound discoveries emerge not from understanding what is present, but from measuring the absence of what we expected to find, transforming the unknown into a catalyst for reimagining the fundamental laws that govern reality itself. In this sense, dark matter represents humanity's frontier of ignorance transformed into scientific opportunity, a reminder that the universe may harbor revelations far stranger than our current theories predict, and that the greatest advances in physics often begin not with answers, but with the humbling recognition that vast domains of reality remain fundamentally beyond our present comprehension. Yet even as we remain ignorant of dark matter's true nature, its gravitational signature has become essential to our understanding of galaxy formation, stellar motion, and the very architecture of the cosmos itself. Imagine standing at the edge of a vast canyon and throwing a ball upward into the air, watching as it rises against gravity, defying the fundamental force that should pull it back down to the earth, and instead of slowing as it reaches its peak, the ball accelerates further upward, faster and faster, disappearing into the sky with no explanation for why the universe itself would behave in such a manner. This is precisely what astronomers discovered in the late 1990s when they observed that the expansion of the universe, rather than slowing down due to the gravitational pull of all the matter contained within it, was actually speeding up, accelerating outward at an increasing rate, as if some invisible force was pushing all the galaxies apart from one another with ever greater force. The physicists called this mysterious phenomenon dark energy, a substance or force that comprises approximately 68% of all the matter and energy in the entire observable universe, yet remains completely invisible to direct observation and defies every conventional understanding of how the cosmos should behave according to the laws of physics that we have spent centuries refining and testing. The mechanism behind our acceptance of dark energy operates through a fundamental principle of modern physics. When observations contradict our theories, we do not discard the observations, we expand our theories to accommodate them, and so dark energy became a placeholder, a mathematical construct inserted into our equations to explain the discrepancy between what we predicted should happen and what we actually measured was happening in the expansion of space itself. We have grown remarkably comfortable with this situation despite its profound philosophical implications, accepting that the universe is primarily composed of something we cannot see, cannot touch, cannot measure directly, and do not understand, treating dark energy with the same casual confidence we might reserve for well-established phenomena like electromagnetism or gravity. Incorporating it into our models of cosmic evolution and the ultimate fate of all existence without any deeper comprehension of its fundamental nature or origin. Perhaps the most humbling aspect of this acceptance is that dark energy may represent not a gap in our understanding that future generations will fill, but rather a fundamental limit to human knowledge itself, a boundary beyond which the universe operates according to principles so alien to our intuition that we may never truly comprehend them, only describe their effects through increasingly sophisticated mathematics that captures their behavior without ever revealing their essence. Yet in this very limitation lies perhaps humanity's greatest strength, our ability to observe, measure, and model phenomena even when their deepest nature escapes us, to build increasingly accurate predictions about the fate of galaxies billions of light years away despite our ignorance of the force driving them apart, suggesting that understanding the universe may ultimately require us to surrender our need for complete comprehension and instead embrace the profound mystery at its heart. Deep within the constellation Centaurus, approximately 5,000 light-years from Earth, exists one of the most peculiar and frigid structures ever observed by modern astronomy, a phenomenon so cold that it has earned the distinction of being the coldest known place in the entire universe. A designation that seems almost paradoxical when one considers that nebulae are typically born from stellar explosions and violent cosmic upheaval that should theoretically generate tremendous heat and energy. The Boomerang Nebula, named for its distinctive curved shape that resembles a returning throwing implement, presents a temperature of approximately 1 degree Kelvin above absolute zero. A coldness so extreme that it actually registers as colder than the background radiation of the cosmos itself, that ancient afterglow of the Big Bang that permeates all of existence. This extreme frigidity arises from a process that contradicts our intuitive understanding of how dying stars should behave, for within this nebula exists a binary star system where one star has shed its outer layers and is now rapidly expanding outward at velocities exceeding 100 kilometers per second, and as these expelled gases rush outward into the vacuum of space, they undergo an adiabatic expansion that causes them to cool to temperatures so low that they seem to defy the natural order of stellar physics, where heat and energy should always predominate over cold and entropy. The mechanism at work here reveals how the universe operates according to principles that remain hidden from casual observation. For when matter expands rapidly into a vacuum without any external energy source to maintain its temperature, the kinetic energy of that expansion translates into motion rather than heat, and thus the particles slow their vibrations to nearly imperceptible levels, creating zones of profound cold that appear to violate the basic expectation that anything born from a star should remain warm. Yet despite our improved understanding of thermodynamics and the physics of adiabatic processes, the Boomerang Nebula continues to perplex observers because it represents an extreme manifestation of principles that we have intellectually accepted while remaining psychologically unprepared for their full implications, revealing once again how the universe contains wonders that persist not because they contradict logic, but because we have failed to truly internalize just how alien and counterintuitive the cosmos can be. And perhaps this is the ultimate lesson that the Boomerang Nebula offers, that our universe operates not according to the dramatic narratives we construct around stellar death and cosmic violence, but rather through subtle mechanisms of thermodynamic transformation that remind us that cold and emptiness can emerge just as readily from the remnants of stellar fire as heat and light themselves. In this way, the Boomerang Nebula stands as a humbling reminder that the universe's most profound mysteries often lie not in cataclysmic events, but in the patient, invisible processes that transform matter and energy according to laws we are only beginning to truly comprehend. Imagine a region of spacetime so dense and so gravitationally powerful that nothing, not even light itself, can escape from beyond its event horizon. And imagine further that this cosmic object slowly evaporates over billions of years by emitting radiation that carries energy away into the void. And in doing so, it gradually loses mass until it disappears entirely in a final burst of light and heat. This is the scenario that Stephen Hawking discovered in 1974, when he demonstrated through quantum mechanical calculations that black holes are not entirely black, but rather emit particles and radiation across all wavelengths, gradually diminishing in size until they vanish completely. Yet here lies one of the deepest paradoxes in theoretical physics. If a black hole contains information about all the matter and energy that fell into it, and if that black hole then evaporates away completely, leaving behind only scattered radiation that appears entirely random and featureless, then where does all that information go? The paradox emerges because the fundamental laws of quantum mechanics demand that information cannot be destroyed or created. It can only be transformed, hidden, or rearranged. Yet the process of black hole evaporation seems to violate this principle by transforming perfectly organized information into apparently random thermal radiation from which the original information cannot be recovered. Physicists have grappled with this contradiction for decades, proposing solutions ranging from the idea that information is somehow encoded within the subtle correlations of Hawking radiation itself, to the notion that black holes do not actually evaporate completely, but leave behind Planck-sized remnants containing all the lost information, to even more radical proposals that involve wormholes, parallel universes, or fundamental revisions to quantum mechanics itself. What makes this paradox so persistent and so fascinating is that it forces us to confront a genuine incompleteness in our understanding, a place where our two most successful theories in physics, quantum mechanics and general relativity, seem to produce mutually exclusive predictions about the fate of information in the universe, and despite decades of brilliant theoretical work, no consensus solution has emerged that satisfies all the constraints and assumptions that physicists believe must hold true. Perhaps the resolution will require us to abandon one of our most cherished assumptions about reality itself, either that information is truly conserved, or that spacetime and gravity are fundamental rather than emergent phenomena, and this willingness to question our deepest principles is precisely what makes the black hole information paradox such a fertile ground for future discoveries in physics. In the deepest mathematical chambers of general relativity, where Einstein's equations govern the fabric of spacetime itself, there exists a theoretical counterpart to one of the universe's most enigmatic objects, a mirror image that flows in precisely the opposite direction, expelling matter and energy rather than consuming it, a concept known as the white hole. Imagine, if you will, a black hole reversed in time, where instead of an event horizon that traps everything beyond its boundary, you would find a point of infinite density from which nothing can ever enter, only emerge, a fountain of creation eternally pushing outward into the cosmos with unstoppable force. The mathematics that describe white holes emerge naturally from the Schwarzschild solution and other solutions to Einstein's field equations, the same elegant framework that predicts black holes themselves, suggesting that if these devouring voids can exist in our universe, their opposite numbers should theoretically exist as well, mathematical mirror twins, separated only by the arrow of time. Yet despite this theoretical symmetry, despite the fact that the equations treat past and future with remarkable equivalence, white holes have never been observed, never been detected, never been conclusively linked to any phenomenon we actually witness in the cosmos, a profound asymmetry between what mathematics permits and what reality seems to allow. The psychological mechanism that keeps white holes alive in scientific discourse, despite their absence from observation, rests upon our deep trust in mathematical beauty and consistency, on the elegant assumption that the universe should balance its equations, that for every cause there should be a corresponding opposite, that symmetry should reign supreme in the laws of nature. We have normalized this absence of evidence by constructing elaborate hypotheses about why white holes might exist but remain forever hidden, proposing that they might be unstable, existing only for infinitesimal moments, or that they might be protected behind event horizons in ways we do not yet understand, or that they might have formed in the early universe but evaporated long ago. And through these successive layers of hypothesis, we maintain a kind of intellectual comfort with the idea that white holes are real even though nothing we observe suggests they are. A remarkable example of how mathematical elegance can sustain belief in phenomena that may ultimately prove to be nothing more than beautiful abstractions divorced from physical reality. This tension between mathematical possibility and empirical silence reveals something profound about the nature of science itself, that our most rigorous theories can generate predictions that remain forever beyond verification, leaving us to wonder whether we are discovering the deep structure of reality or merely exploring the ornate gardens of pure mathematics, a distinction that may ultimately be impossible to draw. Deep within the cosmos, scattered across billions of light-years of space, exist some of the most luminous objects ever observed by humanity. Quasars, which are the brilliant cores of distant galaxies powered by supermassive black holes consuming matter at incomprehensible rates. Astronomers have catalogued thousands of these objects and mapped their positions across the observable universe, expecting them to be randomly distributed throughout space in accordance with the cosmological principle, which states that matter should be evenly spread across vast scales without any preferred direction or clustering pattern. However, beginning in the early 2010s, researchers began noticing something profoundly unsettling when they examined the orientations of quasar jets, which are narrow beams of plasma and radiation ejected from the polar regions of rotating black holes at nearly the speed of light. These jets, which should point in random directions if the universe truly has no preferred orientation, appeared instead to show a remarkable tendency toward alignment, with many quasars in certain regions of the sky exhibiting jets that pointed in similar directions rather than being scattered uniformly as probability theory would predict. This phenomenon became known as the quasar alignment mystery, and it suggested something deeply problematic about either our understanding of the universe's structure or the validity of the fundamental cosmological principle itself. The mechanism behind this unexpected alignment appears connected to the large-scale structure of the universe, including vast filaments of dark matter that form the cosmic web, along with mysterious gravitational influences from regions we cannot directly observe. Some researchers propose that quasars may somehow preferentially form or orient their jets along these cosmic filaments, or that they may be gravitationally influenced by structures so massive and distant that we have not yet detected them, creating what could be called the universe's hidden architecture. The human mind initially resists such findings because they contradict the elegant simplicity we have come to expect from universal laws, where randomness and isotropy provide comfort through their impartiality and scale independence. Yet despite the profound implications of these observations, the quasar alignment mystery remains largely accepted in the scientific community without generating the existential crisis one might expect, and we continue mapping an apparently ordered cosmos while simultaneously asserting that it should be random. Maintaining this cognitive tension as though it represents merely another mystery to be solved rather than evidence that reality itself may operate according to principles far stranger and more interconnected than our current models acknowledge. Perhaps this is the universe's way of revealing that our obsession with finding order in randomness has blinded us to patterns that were always present, waiting for us to develop the instruments and humility necessary to perceive them without the prejudice of our own theoretical expectations. Deep within the cosmic microwave background radiation that suffuses our entire universe, astronomers have discovered something that should not exist according to our current understanding of how the cosmos operates: a peculiar alignment of the largest structures in the observable universe that defies the principle of isotropy, which is the fundamental assumption that the universe looks the same in every direction when viewed on the largest scales. This alignment, christened the axis of evil by physicists who recognized its troubling implications, consists of an unusual orientation of the quadrupole and octupole moments of the cosmic microwave background, essentially meaning that the temperature variations in the radiation left over from the Big Bang are arranged along a specific axis rather than being randomly distributed as our theories predict they should be. When researchers first observed this alignment in the early 21st century, they found that the largest temperature fluctuations in the microwave background appeared to line up with the ecliptic plane of our solar system and the equinoxes of Earth, a coincidence so profound that it seemed to suggest either that our position in the universe was somehow special, or that our measurements were somehow contaminated by our own local circumstances. The psychological mechanism at work here involves our deep-seated tendency to recognize patterns and to assign meaning to alignments, particularly when they intersect with structures we consider significant, such as our own planetary orientation, which creates a kind of cognitive resonance that makes the pattern feel more meaningful than it perhaps ought to feel given the statistical uncertainties involved. Scientists have grappled with multiple explanations ranging from instrumental artifacts and foreground contamination to genuine physics that violates the cosmological principle. Yet the axis persists in the data even as our instruments have become more sophisticated and precise, and rather than disappearing as expected when we accounted for various sources of error, it has only become more statistically significant. We have largely normalized this cosmic puzzle by acknowledging it as an interesting anomaly awaiting further investigation, a kind of acceptable mystery within the scientific framework, yet the core troubling aspect remains unresolved. The universe appears to have a preferred direction, and that direction seems impossibly aligned with our own vantage point on a small rocky planet orbiting an ordinary star. This unsettling coincidence echoes the Copernican principle that dethroned humanity from the cosmic center, Yet here we find ourselves confronted once more with evidence suggesting that our perspective may carry unexpected significance, forcing us to consider whether the universe's fundamental laws might contain hidden symmetries we have yet to comprehend, or whether we are merely pattern-seeking creatures interpreting statistical noise through the lens of our own existential anxieties. In the vast landscape of modern cosmology, there exists a peculiar discrepancy that has come to be known as the Hubble tension, a mathematical disagreement so persistent and troubling that it challenges our fundamental understanding of the universe's expansion and age. The Hubble constant represents the rate at which space itself is expanding, a number that should be measurable and consistent regardless of which method we employ to determine it. Yet when astronomers measure this constant using different techniques, they obtain significantly different results that cannot be easily reconciled or explained away through conventional measurement error or systematic bias. One method, which examines the cosmic microwave background radiation left over from the Big Bang, suggests the universe is expanding at a certain rate, while a completely independent approach using nearby supernovae and distance measurements indicates a notably faster expansion. And this disagreement persists despite decades of refinement, verification, and increasingly sophisticated instrumentation that should have resolved the question definitively. The psychological mechanism underlying our acceptance of this paradox involves a kind of intellectual compartmentalization where scientists acknowledge the tension while continuing their work as though the problem will eventually solve itself through accumulated data. A reasonable approach in many contexts, but one that suggests we have somehow become comfortable with fundamental uncertainty at the core of cosmological understanding. What makes the Hubble tension particularly unsettling is that it cannot be dismissed as mere statistical noise or instrumental limitation, as the measurements have been verified by multiple independent teams using different equipment and methodologies, yet the discrepancy remains stubbornly consistent, creating what might be described as a comfortable crisis where the scientific community accepts the problem without allowing it to fundamentally disrupt the broader framework of accepted cosmological models. This persistent tension suggests that something deeper may be wrong with our current understanding, whether that be an unaccounted systematic error, an incomplete model of dark energy, an undiscovered component of the universe, or perhaps even a need to reconsider fundamental assumptions about how gravity and expansion operate across cosmic scales. Yet we continue to refine our measurements and debate interpretations while the tension endures. A humbling reminder that even our most carefully constructed scientific edifices may harbor fundamental inconsistencies that we have simply learned to live alongside. The resolution of the Hubble tension may ultimately require us to abandon cherished assumptions about the universe's homogeneity or to accept that dark energy evolves in ways our current models fail to capture, a prospect that simultaneously threatens and energizes the cosmological community, for nothing advances science quite like the discovery that our most fundamental measurements cannot be reconciled within existing theoretical frameworks. Deep within the theoretical frameworks that govern our understanding of stellar nucleosynthesis, astronomers have discovered a perplexing discrepancy that challenges one of our most fundamental models of the universe's earliest moments. When scientists observe the abundance of lithium in ancient stars, particularly those formed in the first billion years after the Big Bang, they find that these stars contain roughly 3 times less lithium than the Big Bang nucleosynthesis theory predicts they should contain. This discrepancy, now known as the lithium problem, represents a genuine crack in our cosmic model, a place where observation and prediction diverge in ways that we cannot yet fully explain. The measurements come from spectroscopic analysis of the light these ancient stars emit, a technique that has been refined and verified countless times, and the theoretical predictions emerge from our understanding of how the early universe expanded and cooled, how protons and neutrons combined into the first atomic nuclei. Yet between these two pillars of astronomical knowledge lies this stubborn disagreement, this missing lithium that should be there but somehow is not. The mechanism underlying this mystery operates on a scale that challenges human intuition, existing at the intersection of nuclear physics, stellar evolution, and cosmological theory. In the moments following the Big Bang, when the universe was incomprehensibly hot and dense, specific ratios of light elements formed according to precise quantum mechanical principles, and theoretical calculations suggest that a particular abundance of lithium should have emerged from this primordial furnace. However, the lithium we observe today in old stars appears depleted, suggesting either that our understanding of the early universe's conditions was fundamentally wrong, or that some unknown process destroys lithium in stars more efficiently than we currently believe, or perhaps that our models of how stars mix and churn their internal materials are incomplete in ways we have not yet recognized. Despite decades of investigation by some of the world's most talented astrophysicists, the lithium problem persists in our scientific literature, a reminder that even in an age of sophisticated telescopes and supercomputing power, the universe maintains its mysteries, holding back complete answers and forcing us to confront the boundaries of our knowledge with humility and wonder. Recent observations from space telescopes like Gaia and spectroscopic surveys of globular clusters have only deepened the puzzle, revealing that the lithium depletion pattern varies inconsistently across different stellar populations in ways that defy our current model's predictions, suggesting that multiple competing processes may be at work simultaneously. Some researchers propose that exotic physics beyond our standard model, perhaps involving weakly interacting massive particles or other dark matter candidates, may be destroying lithium in ways classical stellar physics cannot account for, while others suggest that the answer lies not in new physics, but in subtle details of nuclear reaction rates or convective processes we have simply not yet measured with sufficient precision. In the beginning, according to our most rigorous understanding of physics, the Big Bang should have created matter and antimatter in equal quantities, two opposing forces destined to annihilate one another in a brilliant flash of energy the moment they came into contact with each other. Yet here we exist, surrounded by a universe composed almost entirely of ordinary matter, with antimatter relegated to the rarest of phenomena, detectable only in the highest energy cosmic ray collisions and in the controlled environments of particle accelerators. This asymmetry represents one of the deepest mysteries in physics, a fundamental imbalance that should not exist according to the laws of symmetry that govern the subatomic realm, and yet the evidence overwhelms us with its persistence and its profound implications. When scientists observe the behavior of particles and their antimatter counterparts in laboratory conditions, they find that the laws of physics treat them with almost perfect symmetry, suggesting that matter and antimatter should behave identically under identical circumstances. The mystery deepens when we consider that some processes, particularly those involving the weak nuclear force, do exhibit a slight preference for matter over antimatter, a phenomenon known as CP violation, yet even this preference seems far too subtle to account for the dramatic imbalance we observe in the cosmos. Physicists have spent decades constructing increasingly elaborate theoretical frameworks to explain this asymmetry, proposing mechanisms involving supersymmetry, extra dimensions, and modifications to the standard model itself, each one grasping at explanations for why the universe did not simply annihilate itself into pure radiation within the first infinitesimal fractions of a second after its creation. What makes this mystery particularly unsettling is that without this asymmetry, without this inexplicable bias toward matter, there would be no galaxies, no stars, no planets, and no conscious observers to ponder the question in the first place. The universe's apparent fundamental asymmetry remains one of the most humbling reminders of our incomplete understanding, a glaring hole in our physical theories that suggests we have yet to discover something profound about the nature of reality itself. Recent experiments at facilities like CERN's Large Hadron Collider have begun to probe this mystery more directly, examining subtle differences in how matter and antimatter decay. Yet each new measurement seems only to deepen the puzzle rather than resolve it, suggesting that the answer may require us to venture far beyond the comfortable boundaries of our current understanding. Perhaps the resolution lies not in refinements to existing theories, but in fundamentally reconceptualizing how we understand the symmetries of nature itself, a shift in perspective as revolutionary as the transition from Newtonian mechanics to Einstein's relativity. Until that breakthrough arrives, antimatter asymmetry stands as a cosmic koan, a question so profound that its answer may ultimately reshape our comprehension of why anything exists at all. Consider the great rotating disks of galaxies that spin through the cosmic void, their stellar populations orbiting around massive central cores in patterns that should obey the gravitational mathematics we have known for centuries. And yet when astronomers first measured the velocities of stars at the outer edges of these galactic systems, they discovered something profoundly troubling to the foundations of our understanding of physics itself. The stars at the periphery of galaxies were moving far too quickly, maintaining orbital speeds that should have flung them out into the darkness of intergalactic space like stones released from a spinning sling, their gravitational tethers far too weak to contain such velocities. According to the visible matter we could detect, the galaxies simply did not contain enough mass to generate the gravitational force necessary to keep these outer stars in their observed orbits. Yet there they remained, circling with a stubborn consistency that defied explanation. The conventional mathematics that had served us so well in predicting the motions of planets and moons and binary stars seemed to break down entirely when confronted with the vast scales of galactic systems, as though the universe had suddenly decided that the rules no longer applied at these cosmic distances. This contradiction forced scientists to propose the existence of dark matter, an invisible and undetected substance that would comprise the vast majority of each galaxy's mass, providing the additional gravitational anchor required to explain these observations. Yet despite decades of intensive searching, with increasingly sophisticated instruments designed to detect dark matter's presence, we have found no direct evidence of its existence. No confirmation that this mysterious substance is anything more than a mathematical placeholder for our ignorance. We have become so accustomed to building entire cosmological models upon this invisible foundation, accepting dark matter as fundamental reality despite its stubborn refusal to reveal itself through any means we have yet devised. And in doing so, we have perhaps normalized the most profound mystery in modern physics, without fully acknowledging the strangeness of accepting the existence of something we cannot see or measure or touch. Something that comprises most of the universe, yet remains perpetually beyond our grasp. Yet perhaps this very invisibility should give us pause. Perhaps the anomaly itself is telling us something we have not yet learned to hear, that our equations describing gravity and motion across galactic scales remain fundamentally incomplete, and that the universe may operate according to principles we have yet to discover rather than merely hiding its mass in forms we cannot detect. Deep in the vast expanse of space, humanity has sent forth mechanical ambassadors to explore the outer reaches of our solar system, and among these remarkable vessels are the Pioneer spacecraft, which have traveled farther than nearly any other human-made object, crossing billions of kilometers through the cosmic void. Yet these pioneers carry with them a mystery that has puzzled physicists and astronomers for decades, a subtle but persistent deviation from the trajectory that our most sophisticated mathematical models predicted they should follow. The anomaly reveals itself as a gentle but measurable acceleration directed back toward the sun, a deceleration of the spacecraft's outward journey that amounts to only a fraction of a millimeter per second, a force so small that it would be utterly imperceptible in everyday life, yet enormous in its implications for our understanding of the universe and the laws that govern it. Scientists observed that both Pioneer 10 and Pioneer 11, launched in the early 1970s, gradually slowed in their escape from our solar system at a rate that could not be explained by the gravitational pull of the sun, the planets, or any known celestial body, as though some invisible hand was gently pulling these spacecraft backward with a force that defied conventional explanation. The psychological mechanism underlying this mystery lies in our deep reliance on mathematical prediction and our certainty that our equations completely describe physical reality, for we have constructed elaborate frameworks of physics built upon centuries of observation and refinement, frameworks that have proven remarkably accurate in explaining nearly every phenomenon we encounter. When the Pioneer spacecraft began exhibiting this anomalous behavior, it created a profound cognitive dissonance, suggesting either that our equations were incomplete or that some entirely new physical force or phenomenon was at work in the cosmos, operating in ways we had never before imagined or measured. We have normalized this mystery by gradually absorbing it into our expanding conception of what we do not yet understand, assigning teams of researchers to investigate possible explanations ranging from the thermal radiation emitted by the spacecraft itself to dark matter influences to entirely hypothetical gravitational effects. Yet the anomaly persists in occupying a peculiar space between the explained and the inexplicable. A reminder that the universe may harbor secrets far more subtle than we have yet learned to perceive. And perhaps this is the most humbling lesson the pioneers offer us, that even our most distant emissaries, venturing into the darkness beyond the orbit of Neptune, continue to teach us about the limits of our knowledge, serving as silent witnesses to the possibility that nature still guards mysteries in the spaces between our certainties, waiting for future generations to develop the instruments and insights necessary to illuminate what currently remains obscured. When spacecraft travel through the gravitational fields of planets, physicists have long understood exactly how much their trajectories should shift based on the immutable laws of orbital mechanics and gravitational interaction. Yet beginning in the 1990s, astronomers noticed something peculiar occurring during planetary flybys that seemed to violate these fundamental expectations in subtle but consistent ways. The Galileo spacecraft, as it swung past Earth in 1990 to gain speed for its journey to Jupiter, experienced a velocity change that was about 1 millimeter per second faster than all available calculations predicted it should be, a discrepancy so small that it was nearly lost in the margins of measurement error. Yet when similar observations accumulated from other missions including NEAR Shoemaker, Cassini, and Rosetta, the pattern became impossible to ignore, suggesting that something in our understanding of gravity itself might require revision, or that some unknown force was subtly influencing these encounters. Scientists developed numerous hypotheses to explain this phenomenon, ranging from relativistic effects that had been inadequately accounted for in the models, to atmospheric drag that might be pushing the spacecraft slightly harder than expected, to the possibility that the distribution of mass within the Earth or other planets was not quite as uniform as assumed, creating gravitational anomalies that classical calculations failed to predict. Yet none of these explanations achieved complete satisfaction or consistently resolved the discrepancies across all observed cases. The psychological aspect of the flyby anomaly lies in how it represents a profound challenge to scientific certainty, for we have built our entire space program and our understanding of the cosmos upon the bedrock of Newtonian mechanics and general relativity, and when observations persist in contradicting these theories in reproducible, measurable ways, even when the effect is vanishingly small, it forces scientists to confront the uncomfortable possibility that our most fundamental models of reality contain hidden flaws, or that we are missing some crucial ingredient in our physical understanding. What makes this anomaly particularly haunting is its refusal to be pinned down or definitively explained despite decades of careful analysis and increasingly sophisticated measurement techniques, suggesting that some mysteries persist not because we lack the data to solve them, but perhaps because we lack the conceptual framework or the paradigm that would make their solution obvious. It is a humbling reminder that even in an age of unprecedented technological precision, nature retains the capacity to whisper secrets that our current instruments and theories cannot fully articulate. And perhaps the true significance of the flyby anomaly lies not in the anomaly itself, but in what it teaches us about the provisional nature of scientific knowledge and the endless frontier that awaits beyond the boundaries of our present understanding. Deep within the cosmos exist stars that challenge everything we thought we understood about stellar physics and the fundamental nature of matter itself, objects so peculiar that their very existence seems to mock the laws that govern the universe we inhabit. Neutron stars, for instance, represent a category of stellar remnants so impossibly dense that a single teaspoon of neutron star material would weigh as much as an entire mountain on Earth. Yet despite this incomprehensible density, they remain relatively small in diameter, typically only 20 kilometers across, creating a gravitational field so intense that it warps spacetime itself in ways that seem almost magical to our limited perception. Then there are magnetars, an even more extreme variant of neutron star that possess magnetic fields so powerful they would be lethal to any living organism from thousands of kilometers away. Fields so strong they can actually warp the quantum vacuum around them and create phenomena that standard physics struggles to explain adequately. We observe white dwarfs, the dense cores left behind by dying sun-like stars, objects so compact that they are often Earth-sized yet contain the mass of an entire star, defying our intuitive understanding of how matter can possibly be packed so tightly. Quark stars represent the theoretical extreme hypothetical objects where neutrons themselves might be crushed into a soup of fundamental quarks, crossing a boundary into physics we can barely theorize about. Strange stars, named for their hypothetical composition of strange matter, would be even more bizarre, potentially containing strange quarks alongside up and down quarks in configurations that seem to violate everything we consider stable in nuclear physics. Yet as we study these objects with our telescopes and gravitational wave detectors, We continue to observe them, we continue to document them, we continue to incorporate their existence into our models, accepting that the universe contains such impossibilities while we remain fundamentally unchanged, still struggling with mortality and the everyday concerns of our small lives, somehow normalized to the idea that objects defying our deepest understanding populate the heavens above us. Perhaps the greatest strangeness of all is that these objects, born from the violent deaths of massive stars, may represent stable configurations of matter that could persist for trillions of years, outlasting galaxies themselves, silent monuments to physics operating at scales and densities where our equations finally break down and admit their own limitations. And yet, for all our theoretical frameworks and observational data, we cannot help but wonder whether these exotic objects might harbor secrets we have yet to imagine. Perhaps strange stars serve as cosmic laboratories where matter achieves states of organization so alien that they would fundamentally reshape our understanding of what is possible in a universe that seems determined to exceed the boundaries of our comprehension. Deep within the hearts of neutron stars, where gravity has compressed matter to its absolute breaking point, exists a state of being so extreme that it challenges our fundamental understanding of what matter can become. At densities that exceed even those found in ordinary neutron star material, the very structure of atoms collapses entirely, and protons and neutrons themselves break apart into their constituent components, quarks and gluons. This exotic substance, known as quark matter, represents a phase of matter that exists under conditions so intense that ordinary atomic bonds become meaningless, and what remains is a seething soup of fundamental particles bound together by the strong nuclear force in ways that physics can barely describe. The strange thing about quark matter is that despite being composed of the most basic building blocks of reality, it exhibits properties that seem almost impossible, including the potential for color superconductivity, where quarks pair together in ways that eliminate resistance and create a frictionless quantum state. We theorize that quark matter might exist in the deepest cores of the densest neutron stars, yet we have never directly observed it, and perhaps never will, given the cosmic distances involved and our inability to recreate such conditions in any laboratory on Earth. What is remarkable is that this substance, if it truly exists, would represent a sort of cosmic extremism where the fundamental rules we associate with matter become almost unrecognizable, yet we continue to theorize about its properties with considerable confidence. The persistence of quark matter in our scientific understanding, despite its inaccessibility, speaks to something profound about how we approach physics itself. We accept the possibility of states of matter we may never touch or measure directly, trusting in the logical frameworks of quantum mechanics and relativity to guide us toward truth, and this acceptance allows our minds to comprehend the universe in its most violent and extreme manifestations. In this way, quark matter becomes more than a mere theoretical curiosity. It becomes a window into how science itself operates at the boundaries of human knowledge, where imagination and mathematical rigor must substitute for direct observation, and where the acceptance of uncertainty paradoxically strengthens rather than weakens our grasp of physical reality. And perhaps this is why quark matter captivates us so completely. It stands as a testament to the power of theoretical physics to illuminate the universe's darkest corners, reminding us that the most profound truths about reality often lie beyond the reach of our instruments, waiting patiently in the crushing depths of distant stars for a future generation of physicists to unveil their secrets. Perhaps it is this very humility, this willingness to explore realms we cannot directly access, that distinguishes science from mere speculation, transforming quark matter from an abstract mathematical construct into a meaningful probe of nature's deepest organizational principles. Imagine a world without a sun, a planet cast adrift in the infinite darkness of space, orbiting nothing, bound to nothing, moving through the cosmos as a solitary wanderer in the vast emptiness between stars. These objects, known as rogue planets or nomad planets, are worlds that have been ejected from their original stellar systems through gravitational encounters with other planets or massive bodies, leaving them untethered from any star and condemned to an eternal journey through the interstellar void. Astronomers estimate that there may be more rogue planets than stars in our galaxy, perhaps trillions of these orphaned worlds drifting silently through space, invisible to our telescopes because they emit no light of their own and reflect none from a distant sun. The surface of a rogue planet would present a landscape of absolute desolation, where temperatures plummet to nearly absolute zero, where no photosynthesis occurs, No light penetrates the perpetual darkness. And yet somehow these worlds continue their solitary voyages across millions of years without a source of warmth or energy. The psychological mechanism that makes rogue planets so compelling to contemplate is rooted in our fundamental understanding of planetary formation and orbital mechanics, which teaches us that planets must form around stars and remain bound to them by gravitational attraction, making the very existence of free-floating worlds seem paradoxical and unsettling. Yet we have come to accept rogue planets as inevitable consequences of dynamic stellar systems where gravitational interactions are common, where three-body problems create unstable configurations, and where the ejection of planetary bodies is not an anomaly, but rather a natural outcome of cosmic evolution. The persistence of these mysterious objects in our understanding of the universe represents a profound shift in how we conceptualize planetary systems, moving away from the orderly, stable configurations we once imagined toward a cosmos far more chaotic, violent, and populated with castaways than our predecessors ever supposed. Some of these wanderers may retain sufficient internal heat from their formation to harbor subsurface oceans beneath frozen crusts, potentially creating refuges for microbial life in the absolute darkness, while others, massive enough to sustain thermonuclear fusion in their cores, blur the distinction between planet and star, existing in a liminal space that challenges our taxonomies and reminds us that the universe defies easy categorization. The discovery of rogue planets has fundamentally altered our conception of habitability itself, suggesting that life need not depend on the warmth of a nearby star, but might instead flourish in the thermal energy generated by planetary cores or sustained through chemosynthesis in hidden subsurface seas, expanding the boundaries of where we might someday search for extraterrestrial existence. The detection of these solitary worlds through infrared observations and gravitational microlensing has revealed that our galaxy teems with far more planetary diversity than stellar systems alone could produce, fundamentally reshaping our understanding of how common planets truly are in the universe. In the vast expanse beyond Neptune's orbit lies one of the most captivating mysteries in modern astronomy, a gravitational phantom that astronomers call Planet 9, a celestial body that has never been directly observed through a telescope, yet whose influence seems to ripple through the outer solar system like invisible waves across a dark ocean. The discovery of this hypothetical world began in 2014 when researchers noticed something profoundly unusual about the orbits of distant trans-Neptunian objects, small icy bodies that cluster and move in ways that standard gravitational models cannot adequately explain. These objects, scattered throughout the Kuiper Belt and beyond, follow trajectories that suggest something massive is hurting them, pulling at them with an invisible hand, causing their orbits to align in patterns too organized to be random, yet too peculiar to match any known planet within our solar system. The mathematical evidence suggests that Planet 9, if it exists, would be a super-Earth or mini-Neptune roughly 10 times the mass of our world, dwelling in an orbit so distant and elongated that it completes a single journey around the Sun approximately every 10 to 20,000 years. The psychological mechanism that makes this mystery so compelling lies in humanity's deep need to solve cosmic puzzles through logical deduction, to use mathematical patterns as breadcrumbs leading toward hidden truths that lurk beyond our current observational reach. Scientists find themselves in the peculiar position of arguing for the existence of something they cannot see, defending a hypothesis with gravitational calculations and orbital statistics, while simultaneously acknowledging that the object might not exist at all, that alternative explanations involving massive asteroid collisions or ejected planetary cores might better account for what we observe. This paradox persists because the scientific method demands that we pursue mysteries wherever evidence leads us, even when that evidence is indirect, circumstantial, and frustratingly incomplete, creating a space where rigorous inquiry meets the humbling awareness that the universe still harbors countless secrets waiting to be unveiled. Yet as telescopes grow more sophisticated and survey techniques improve, the hunt for Planet 9 intensifies, with astronomers scanning the infrared signatures and gravitational disturbances across vast stretches of sky, holding fast to the possibility that what remains hidden today may finally reveal itself tomorrow, transforming speculation into certainty and reminding us that the greatest discoveries often emerge from our willingness to believe in what we cannot yet see. The historical parallel to this quest resonates deeply. Just as Neptune was mathematically predicted before its visual confirmation in 1846, Planet 9 represents a modern continuation of astronomy's greatest tradition, where reason and observation dance together in pursuit of cosmic truth, suggesting that patience and rigorous methodology remain humanity's most reliable tools for penetrating the darkness that surrounds our small corner of the universe. In the autumn of 1991, a cosmic ray detector stationed in Utah picked up something so extraordinarily energetic that physicists across the world struggled to comprehend what their instruments were telling them. A single subatomic particle traveling through the vast emptiness of space that carried approximately 50 joules of kinetic energy, which is roughly equivalent to the energy of a baseball pitched by a professional athlete. Except this energy was concentrated into something billions upon billions of times smaller than even that baseball, a phenomenon so improbable that the scientists involved actually named it after their own incredulous reaction, dubbing it the "oh my god" particle because no other designation could adequately express their genuine shock. According to the established laws of physics that we have come to understand through decades of experimental validation and theoretical refinement, cosmic rays should have a maximum possible energy level beyond which they simply cannot travel through the universe, a theoretical ceiling known as the Greisensatzeping-Kuzmin limit. A boundary that suggested that ultra-high-energy particles from distant galaxies would lose their energy through interactions with the cosmic microwave background radiation permeating all of space. And yet this singular particle appeared to have exceeded that limit, arriving at Earth with an energy level that seemed to violate everything physicists thought they knew about the fundamental constraints governing the cosmos. The mechanism behind this mystery hinges upon the deepest questions about whether our understanding of cosmic physics remains incomplete, whether some unknown phenomenon or exotic process occurs in the universe that allows particles to maintain or even gain energy across incomprehensible distances, or whether detection errors and misinterpretations somehow skewed the measurements, though subsequent observations have suggested that such ultra-high-energy particles do indeed exist. Arriving at our planet with inexplicable regularity despite the theoretical barriers that should prevent their existence. What remains most striking is how seamlessly this cosmic anomaly has been integrated into our scientific understanding, how we have simply expanded our models and expanded our theories rather than letting this defiance of predicted limits fundamentally shake our confidence in physics itself, demonstrating our remarkable capacity to absorb impossibilities into the landscape of accepted knowledge. To acknowledge that the universe still possesses mysteries at the furthest edges of our comprehension. Perhaps this is the universe's way of reminding us that even our most rigorous theories are merely provisional frameworks, elegant scaffolding we construct to organize what we observe, and that the moment we believe we have finally grasped the fundamental rules, reality introduces us to a particle traveling at nearly the speed of light, carrying the energy of a fastball, and whispers that there is still so very much we do not understand. Deep within the cosmos, traveling at nearly the speed of light, exist particles so energetic and so rare that they seem to mock our fundamental understanding of physics itself. And these are the ultra-high-energy neutrinos, ghostly messengers from the most violent events in the universe that carry energies millions of times greater than anything we can produce in our most powerful particle accelerators on Earth. These neutrinos originate from sources both known and mysterious, emerging from the cores of active galactic nuclei where supermassive black holes devour entire stars, from the jets of gamma-ray bursts that briefly outshine entire galaxies, and from sources we have yet to identify or comprehend, traveling through the void of space with such tremendous momentum that they punch through entire planets and our bodies without any interaction whatsoever. The fascinating puzzle lies in understanding how the universe itself generates such inconceivable energy in the first place, requiring mechanisms so extreme and so catastrophic that even our most sophisticated theoretical physics struggles to fully account for them. And yet we observe these ultra-high-energy neutrinos arriving at Earth's surface regularly enough that we have constructed massive detectors buried deep underground and in polar ice to capture these rare cosmic visitors. What makes this phenomenon psychologically compelling is that we have normalized the concept of the impossible, accepting without significant wonder that the universe contains energy sources generating particles with energies beyond anything we thought feasible, and we have built elaborate scientific frameworks and experiments to study something that defies our intuitive understanding of how energy and physics should behave. Despite decades of observation and theoretical work, we still cannot fully explain the origins of the highest energy neutrinos, suggesting that somewhere out in the cosmos, processes occur that we have not yet discovered or theorized, and we continue detecting these ultra-high energy neutrinos with quiet scientific certainty. Treating the unexplainable as merely another unsolved puzzle awaiting future investigation, rather than acknowledging the profound strangeness of these particles that traverse existence itself. The IceCube Neutrino Observatory in Antarctica has detected neutrinos with energies exceeding 1 petaelectronvolt, a threshold so extreme that a single particle carries the kinetic energy of a professional baseball thrown at full speed. Yet these cosmic messengers arrive so infrequently that we must wait months between detections, a humbling reminder that despite our technological sophistication, the universe operates on scales of rarity and power that reduce our instruments to patient witnesses rather than active interrogators of cosmic truth. And perhaps this is the universe's way of teaching us humility, that for all our instruments and equations, some of its most energetic phenomena remain shrouded in mystery, their sources hidden behind cosmic distances and our own limited ability to observe, reminding us that the act of discovery itself requires patience that matches the rarity of the phenomena we seek to understand. Deep within the cosmos, scattered across billions of light-years of space, astronomers have detected some of the most violent and enigmatic electromagnetic events in the universe, phenomena lasting mere milliseconds, yet releasing more energy than our sun produces in an entire year. Events we have come to call fast radio bursts, or FRBs as they are known in scientific literature. These extraordinary signals arrive at Earth as brief, intense pulses of radio waves, appearing suddenly and without warning from seemingly random locations in the sky. And what makes them profoundly mysterious is that despite decades of observation and countless hours of telescopic scrutiny, we still cannot definitively explain what creates them or why they exist at all. When astronomers first detected these signals in 2007, they assumed they were merely local phenomena, perhaps interference or instrumental errors within our own instruments. But as detection methods improved and multiple independent observatories confirmed these bursts from different parts of the world, the scientific community was forced to confront an uncomfortable reality. Something genuinely strange and powerful was happening in the distant universe. The bursts vary tremendously in their characteristics, some repeating from the same location while others appear to be singular events, some arriving in clusters while others are isolated, and this incredible variability suggests that perhaps multiple different mechanisms could be producing them, or alternatively, that we are witnessing the same phenomenon expressed through fundamentally different physical conditions and environments. Leading theories propose magnetars, those exotic neutron stars with magnetic fields billions of times stronger than anything we can create on Earth, as potential sources, while other scientists suggest colliding neutron stars, black holes consuming stellar material at extreme rates, or even more speculative phenomena involving the collision of cosmic strings or other exotic matter we have yet to fully understand or even confirm exists. What strikes us most profoundly about fast radio bursts is how they exemplify our persistent inability to comprehend the universe despite our technological advances, how even with our most sophisticated instruments and our deepest mathematical frameworks, we encounter phenomena that refuse to fit neatly into our existing categories of understanding, and yet we continue observing them, cataloging them, searching for patterns. Treating this fundamental mystery as though it were simply another problem awaiting solution, as though the universe will eventually yield its secrets if we simply persist long enough in our investigations. And indeed, with each passing year, new observatories come online and detection rates accelerate, bringing us closer to that moment when the pattern finally emerges from the noise, when some brilliant mind synthesizes the scattered observations into a coherent theory, and fast radio bursts transform from cosmic mystery into understood phenomenon, another chapter in our ever-expanding encyclopedia of the universe's true nature. Deep in the cosmos, there exist objects so extraordinarily dense and magnetically powerful that they represent perhaps the most extreme manifestation of magnetism known to physics. And these are the magnetars, neutron stars with magnetic fields so intense that they would strip the iron from your blood from thousands of kilometers away. Yet what makes them truly enigmatic are the violent flares they produce. Sudden and catastrophic releases of energy that can illuminate distant galaxies, and yet remain fundamentally mysterious in their generation and behavior. When a magnetar erupts in a flare, it releases more energy in a fraction of a second than our sun will emit over the course of millions of years. A convulsion of magnetic force so tremendous that it warps spacetime itself and sends cascading waves of radiation across the electromagnetic spectrum in wavelengths that range from radio waves to gamma rays of such intensity that they would be lethal to any organism at vast distances. The mechanism driving these explosions appears to involve the catastrophic reorganization of the magnetar's impossibly twisted magnetic field lines, a process where accumulated magnetic tension suddenly ruptures and reconfigures, releasing gravitational energy stored in the very geometry of space around the object. Yet scientists remain genuinely uncertain about the precise mechanics of how these fields become so unstable and why they erupt with such ferocity and irregularity. What persists as particularly vexing is that magnetar flares seem to violate our intuitive understanding of how magnetic fields should behave, defying predictions from conventional magnetohydrodynamic models, and suggesting that phenomena at extreme densities and magnetic strengths operate under principles that our current theoretical frameworks struggle to adequately describe or predict, leaving these neutron star outbursts as witnesses to physics at its most alien and unexplained. In December 2004, the magnetar SGR 180620 unleashed a flare so powerful that it temporarily saturated satellites orbiting Earth despite the source lying 50,000 light-years distant. A sobering reminder that even from inconceivable distances, these objects can still shake our instruments and our confidence in understanding the universe's most violent extremes. Each magnetar flare thus serves as a humbling cosmic experiment, one that continues to challenge our theories and beckon us toward a deeper comprehension of matter and energy in regimes where the laws of physics themselves seem to bend. The observation of these celestial tempests has revolutionized our understanding of magnetic reconnection and plasma physics, offering laboratories where theoretical predictions can be tested against nature's most extreme experiments, while simultaneously revealing that the universe still guards profound secrets within the hearts of its most compact and violent objects. Deep in the cosmos, there exist phenomena so violent and so energetic that they release more energy in a single second than our sun will produce over its entire 10 billion-year lifetime. And these catastrophic events are known as gamma-ray bursts, sudden and intense flashes of gamma radiation that appear to come from random directions across the sky with no warning whatsoever. When astronomers first detected these mysterious bursts using satellite instruments in the 1960s, they were completely baffled by their origins, as the bursts appeared for mere seconds or minutes before vanishing entirely, leaving behind no visible counterpart and no obvious source that could account for such tremendous energy output. The initial hypothesis suggested that these events might originate from nuclear weapons detonating in Earth's upper atmosphere or from Soviet military activity, a suspicion that persisted for years as the scientific community struggled to explain what they were observing in the depths of space. As technology improved and more sensitive detectors captured additional bursts, astronomers began to recognize that gamma-ray bursts occurred far beyond our solar system, yet the fundamental question of their origin remained deeply unresolved and profoundly mysterious. The leading theories proposed that these bursts resulted from the catastrophic collapse of massive stars at the ends of their lives, violent mergers between neutron stars or black holes, or perhaps exotic phenomena entirely outside the standard model of stellar physics and cosmic evolution. What makes gamma-ray bursts particularly puzzling is that no single explanation seems sufficient to account for all observed varieties, as some bursts are brief and appear connected to compact object collisions, while others are longer and seem associated with dying massive stars, suggesting that multiple distinct mechanisms might be producing these devastating cosmic explosions. The energy requirements alone defy easy explanation, as the physics necessary to accelerate particles to relativistic speeds and generate such phenomenal radiation seems to require extreme conditions that push our understanding of matter and energy to their absolute limits. Despite decades of observation with increasingly sophisticated instruments and theoretical modeling by some of the brightest minds in physics and astronomy, the precise mechanisms that trigger gamma-ray bursts and the complete catalog of all possible origins remain enigmatic, illustrating how nature continues to produce phenomena that exceed our current comprehension and humble our confidence in understanding the fundamental workings of the universe. Yet recent observations from telescopes like Swift and Fermi have begun to illuminate this darkness, detecting the faint afterglows that follow these bursts and revealing tantalizing clues about their progenitors, while gravitational wave detectors have now confirmed that at least some gamma-ray bursts do indeed arise from the violent merging of compact objects, finally validating decades of theoretical predictions and opening new windows into understanding these most extreme events in the cosmos. Deep within the cosmic web that structures our universe, astronomers have discovered something that challenges our fundamental understanding of how matter should be distributed across space. A massive region of emptiness known as the KBC void, named after the initials of the three astronomers who first mapped its extraordinary proportions. This void, which encompasses a sphere of space roughly 2 billion light-years in diameter, with our own Milky Way galaxy positioned near its center, represents a region containing far fewer galaxies than the cosmic average. A deficiency so profound that it fundamentally contradicts what we would expect from our current models of universal expansion and galaxy formation. When cosmologists peer outward from Earth using our most powerful telescopes, they observe that beyond approximately 500 million light-years distant, the void begins to give way to the normal cosmic web structure. But within this immense bubble of relative emptiness, galaxy density remains mysteriously and dramatically reduced. The psychological and observational mechanism that allowed this void to remain undetected for so long stems from humanity's particular vantage point within the cosmos. For we inhabit a location so deeply embedded within this void that detecting it required decades of careful astronomical surveys and sophisticated three-dimensional mapping of galaxy distributions across billions of light-years. Our position near the center of this cavity meant that we naturally observed relatively fewer galaxies in all directions, a pattern so uniform that it appeared normal, blending seamlessly with our expectations of cosmic homogeneity. Yet when scientists finally recognized this pattern as genuinely anomalous rather than mere random variation, it presented a profound puzzle for modern cosmology. The KBC void persists as a cosmic mystery despite overwhelming evidence of its existence, because explaining its origins within standard cosmological theory remains extraordinarily difficult, requiring us to either invoke rare statistical fluctuations in an otherwise uniform universe or to fundamentally reconsider our understanding of how voids form and persist across cosmic time. Some researchers propose that the void may have formed from density fluctuations amplified by dark energy over billions of years, while others suggest that encounters between ancient galaxy clusters might have swept material outward, leaving this curious scar in the fabric of spacetime that continues to perplex those who study the universe's largest structures. What makes the KBC void particularly humbling is that it serves as a reminder of our cosmic provincialism. We inhabit not a typical region of the universe, but rather an extraordinary anomaly, suggesting that our observations of the cosmos may be fundamentally skewed by our singular perspective, a bias that future generations of astronomers studying distant galaxies may need to carefully account for in their models of universal structure and evolution. In the vast expanse of the observable universe, spanning approximately 10 billion light-years across the cosmic void, there exists a structure so incomprehensibly enormous that it challenges our fundamental understanding of how matter should be distributed throughout space. This is the Hercules-Corona Borealis wall, a cosmic structure discovered through careful observation of galaxy distributions that appears to be the largest coherent structure known to exist in the universe. When astronomers mapped the positions of galaxies and quasars across billions of light-years of space, they noticed something profoundly unexpected. These objects were not scattered randomly but arranged in a vast web-like pattern, and at the center of this pattern lay an enormous wall of galaxies stretching across distances so great that light itself would require 10 billion years to traverse it. The structure was identified through the distribution of gamma-ray bursts, those violent and distant cosmic explosions that serve as beacons marking the locations of the most remote galaxies and ancient quasars in the universe. The theoretical models that physicists and cosmologists have constructed over decades suggest that matter in the universe should reach a kind of homogeneity at sufficiently large scales, meaning that when you zoom out far enough, everything should look relatively uniform and evenly distributed in all directions. This concept forms the foundation of modern cosmological theory, the cosmological principle itself, which states that on the largest scales the universe appears essentially the same regardless of where you observe from or in which direction you look. Yet the Hercules-Corona Borealis wall stands in apparent defiance of this principle, presenting itself as an anomalous concentration of matter on scales that should theoretically be too large for such structures to exist or persist. The mere existence of something so vast creates logical tensions in our models and forces us to confront the possibility that our understanding of cosmic structure formation remains fundamentally incomplete in ways we have not yet fully recognized or accepted. Perhaps most unsettling is that this wall may not be unique. Other candidates for similarly vast structures have emerged from more recent surveys, suggesting that the universe might be riddled with such anomalies at scales where we never expected to find them, transforming what we once considered impossible into an urgent scientific mystery demanding new theoretical frameworks. As astronomers continue to scrutinize the deepest surveys of the cosmos, they grapple with a humbling question. If structures of such staggering magnitude can exist at scales where they should not, what other fundamental assumptions about the universe might we be forced to reconsider, and how much of what we call cosmic law is merely the temporary boundary of our current ignorance? In the observable universe, astronomers have discovered a category of galaxies that presents one of the most perplexing challenges to our understanding of cosmic structure, entities known as dark galaxies, which are believed to exist throughout space, yet remain almost entirely invisible to our most powerful telescopes and detection instruments. These dark galaxies are thought to be collections of stars and stellar material distributed throughout regions of space, where conventional observation methods fail to reveal their presence, not because the stars themselves are absent, but because the galaxies lack the luminous structures that typically make galaxies detectable, such as bright active galactic nuclei, prominent stellar disks, or regions of intense star formation that would normally produce the electromagnetic radiation we use to identify and study galaxies. The mechanism behind their invisibility relates to the distribution and composition of their stellar populations, which may consist predominantly of older, dimmer stars that produce comparatively little light. Or alternatively, they may contain vast quantities of dark matter arranged in configurations that simply do not concentrate enough visible light in any particular direction to register above the threshold of detectability with current observational technology, making them effectively ghosts within the cosmic framework. What makes dark galaxies particularly mysterious is that they should theoretically contain significant quantities of hydrogen gas and other stellar material. Yet this material somehow remains largely dormant or isolated from the processes of vigorous star formation that characterize more observable galaxies, suggesting that either our models of galaxy formation are incomplete, or that dark galaxies represent a phase of galactic evolution that we do not yet fully comprehend. Astronomers persist in their efforts to locate and study dark galaxies despite the fundamental difficulty of their detection, because their existence has profound implications for understanding how much matter actually exists in the universe, how that matter distributed itself across cosmic time, and whether our current census of galactic populations represents only a small fraction of what truly exists beyond our observational reach. Yet we have largely normalized this uncertainty and continued with our cosmological models, despite knowing that a potentially enormous population of galaxies may exist completely unknown to us. Recent indirect evidence from gravitational lensing studies and the anomalous rotation curves of nearby galaxy clusters has suggested that dark galaxies may be far more numerous than previously estimated, potentially outnumbering visible galaxies by a factor of 10 or more, which would fundamentally reshape our understanding of the universe's structure and composition in ways we are only beginning to appreciate. Such a revelation would necessitate a comprehensive reassessment of our models regarding dark matter distribution, galaxy formation timelines, and the true density of the universe, compelling astronomers to reconsider fundamental assumptions about cosmic evolution that have guided decades of research and observation. Deep within the universe, astronomers have discovered something that challenges our fundamental understanding of how galaxies form and evolve, a phenomenon they have come to call ghost galaxies, vast collections of stars that appear to exist in a state of profound emptiness and invisibility despite their considerable mass and presence in the cosmos. These are galaxies that contain trillions upon trillions of stars, structures so enormous that they dwarf even our own Milky Way. And yet they remain nearly invisible to our telescopes and our observations, appearing as faint wisps or barely perceptible structures against the darkness of space. What makes ghost galaxies so profoundly mysterious is that they seem to contradict everything we know about how star formation should work in the universe. For according to our models and theories, galaxies of such immense size should be burning with brilliant light, their countless stars creating an intense glow that would easily be detected from Earth. And yet these structures remain stubbornly dim, elusive, and difficult to observe even with our most advanced instruments. The mechanism behind this cosmic invisibility appears to involve an unusual distribution of stellar material within these galaxies, where stars are spread so thinly and diffusely throughout their enormous volumes that their combined light becomes spread across such vast distances that it becomes nearly imperceptible, creating what astronomers describe as extremely low surface brightness galaxies. Structures where the stars exist but are separated by such tremendous gulfs of emptiness that they produce minimal illumination across any given area of space. The persistence of ghost galaxies in our universe presents a profound puzzle because they suggest that the cosmos contains far more stellar matter than our current census of visible galaxies would indicate, implying that we have been systematically undercounting the number of stars and galaxies that actually exist, and that our entire understanding of cosmic structure and evolution may be incomplete or fundamentally biased toward observing only the most luminous and obvious objects while remaining blind to vast populations of quieter, dimmer structures that populate the space between what we can easily see. Recent observations from advanced telescopes like the Hubble Space Telescope and ground-based surveys have begun to unveil these hidden worlds, revealing that ghost galaxies may constitute a significant fraction of the universe's total galactic population, fundamentally reshaping our understanding of cosmic demographics and suggesting that the universe is far richer and more complex than our previous limited perspective allowed us to perceive. These discoveries have profound implications for our understanding of dark matter distribution, galaxy formation timescales, and the ultimate fate of the universe itself, suggesting that the cosmos harbors far greater complexity and hidden structure than we had previously imagined, and compelling astronomers to develop new observational techniques and theoretical frameworks capable of accounting for these elusive stellar populations that inhabit the dimmer regions of our expanding universe. Deep within the cosmos exist celestial objects that occupy one of the most profound positions in astronomical understanding, occupying the strange liminal space between planets and stars themselves, and these fascinating entities are known as brown dwarfs, sometimes referred to as failed stars. When massive clouds of gas and dust collapse under their own gravity to form new stellar objects, they require a minimum mass threshold of approximately 80 times the mass of Jupiter in order to ignite hydrogen fusion in their cores, the fundamental process that defines a true star. Brown dwarfs are objects that have accumulated enough mass to achieve some degree of gravitational compression and internal heat generation, sometimes reaching temperatures of several thousand degrees Kelvin, yet they fall tantalizingly short of that critical threshold necessary for sustained hydrogen fusion. What makes brown dwarfs particularly fascinating is that they undergo deuterium fusion, a process involving a heavier isotope of hydrogen that requires significantly lower temperatures than standard hydrogen fusion, allowing them to briefly illuminate their surroundings before gradually cooling over billions of years. The psychological impact of understanding brown dwarfs stems from their liminal nature, existing at the boundary between two fundamental categories of cosmic objects, challenging our human tendency to organize the universe into neat, clearly defined classifications. They represent a kind of cosmic disappointment, objects that came so close to achieving stellar status, yet remain fundamentally separate, a reality that resonates with our intuitive understanding of thresholds and near misses in existence. Despite accumulating substantial scientific knowledge about brown dwarfs and their prevalence throughout the galaxy, we continue to regard them with a sense of incompleteness, viewing them through the lens of what they failed to become rather than celebrating what they actually are. This persistent tendency to judge these objects by their failure to cross an arbitrary mass boundary, rather than recognizing their unique properties and their abundance in stellar neighborhoods throughout the observable universe, demonstrates how deeply human concepts of success and failure permeate even our most objective scientific endeavors. In studying brown dwarfs, we are ultimately confronted with a mirror of our own species' relationship with limitation and potential, forced to reckon with the question of whether significance requires conformity to pre-established definitions, or whether value might exist in occupying spaces that defy easy categorization. Perhaps the greatest lesson these objects offer is that the universe's most intriguing phenomena often emerge not from achieving predetermined thresholds, but from the unique conditions that arise at the boundaries between them. In the realm of theoretical physics, one of the most profound and unsettling possibilities emerges from the equations of general relativity, which permit the existence of closed timelike curves, pathways through spacetime that would allow an object or observer to travel backward through time and potentially arrive at an event that occurred before their departure. Stephen Hawking, confronted with the logical paradoxes and causality violations that such time travel would produce, proposed in 1992 what he termed the chronology protection conjecture, a speculative principle suggesting that the laws of physics themselves contain some unknown mechanism that prevents the formation of these closed timelike curves, and thereby protects the universe from the grandfather paradox and other temporal contradictions that would make reality fundamentally incoherent. The conjecture does not claim to prove that time travel is impossible, but rather proposes that nature operates under some hidden constraint, some yet undiscovered law or quantum effect that actively prevents any configuration of matter and energy from ever creating the conditions necessary for causality violations to occur. This represents a profound recognition that if the equations of general relativity truly allow time machines, then either those equations are incomplete, or nature must possess a remarkable ability to impose restrictions on what the equations technically permit. The conjecture persists within theoretical physics despite lacking empirical evidence and despite the absence of any proven mechanism that would enforce such protection, residing instead in a realm of mathematical speculation and logical reasoning about what a self-consistent universe would require. Scientists continue to examine this idea not because they have observed its effects, but because the alternative, a universe in which time travel and causality violations are possible, seems to demand some explanation for why we observe a reality that adheres so strictly to cause preceding effect, a world in which the past remains fixed and immutable, where history cannot be rewritten by future actions traveling backward along the arrow of time. Whether through quantum decoherence, the formation of event horizons that isolate closed time-like curves from the rest of spacetime, or some entirely unforeseen principle yet to be discovered, the universe appears to possess an elegant self-consistency that forbids paradox, suggesting that reality itself may be fundamentally protected against its own logical impossibilities. Yet this protection, if it exists, may not operate through prohibition alone. It might instead manifest as a kind of cosmic censorship, wherein the very act of constructing a time machine would trigger consequences, Hawking radiation, quantum instability, or gravitational collapse, that render the device inoperable before it could function, suggesting that nature achieves consistency not through forbidding certain configurations, but through their inevitable self-destruction at the moment they threaten causality. Imagine a pathway through the fabric of spacetime itself that loops back upon itself, a trajectory so extraordinary that it would allow a particle or even a conscious being to travel forward through time, arrive at a destination, and then continue along a curve that bends back to the very moment from which it departed, creating a closed loop where the traveler becomes their own ancestor and descendant simultaneously. This is the concept of a closed time-like curve, a mathematical possibility that emerges directly from Einstein's field equations of general relativity, those elegant expressions that describe how gravity warps the very nature of space and time around massive objects. The mathematics does not forbid these structures, and this fundamental allowance creates a profound paradox that has haunted theoretical physicists for nearly a century. For if such curves genuinely exist in the universe, then causality itself becomes negotiable, and all our intuitions about the linear progression of cause and effect dissolve into logical contradiction. The psychological mechanism that permits us to discuss closed time-like curves as serious scientific objects, despite their apparent impossibility within our experience, rests upon a peculiar human capacity to hold two incompatible truths simultaneously in our minds. We accept that the mathematics of general relativity is extraordinarily successful at describing black holes and gravitational waves and the expansion of the universe itself. Yet we refuse to accept that these same equations might actually permit backward time travel. We live within this intellectual tension by compartmentalizing, by assigning closed timelike curves to the category of mathematical curiosities rather than physical realities, suggesting that perhaps some unknown constraint or some deeper principle that we have yet to discover must forbid them from actually forming in nature, even though nothing in the equations explicitly prevents them. And yet, despite this deliberate skepticism, we continue to study them, to write papers about them, to explore the paradoxes they generate, maintaining a kind of resigned fascination with structures that mathematics says could exist, but logic insists should not. A tension that persists because neither physics nor philosophy has managed to offer a fully satisfying resolution. Some physicists have proposed elegant resolutions. The Novikov self-consistency principle suggests that any actions taken by a time traveler would be automatically constrained to remain logically consistent with the past, while others invoke the many worlds interpretation to suggest that closed timelike curves might branch reality into parallel timelines, allowing causality to remain intact even as the loops themselves remain mathematically valid. Yet these solutions, however ingenious, amount to adding new theoretical scaffolding to prevent a catastrophe that the equations themselves never explicitly warned us about, leaving the fundamental mystery intact. Why does nature appear to forbid something that its deepest mathematical laws seem to permit? Wormholes represent one of the most fascinating and perplexing theoretical constructs in modern physics, existing as mathematical solutions to Einstein's field equations that describe the very fabric of spacetime itself. These hypothetical tunnels would theoretically connect two distant points in the universe, potentially allowing for shortcuts through space and time that would otherwise require traveling across unimaginably vast distances through conventional means. The concept emerged from the mathematics of general relativity in the early 20th century, when physicist Karl Schwarzschild discovered solutions to Einstein's equations that implied the existence of bridges between different regions of spacetime, though these mathematical entities remained largely abstract and speculative. The fundamental mechanism behind wormholes relies on the idea that spacetime, rather than being a fixed and immutable backdrop for the universe, is itself a dynamic structure that can bend, curve, and fold in response to the presence of matter and energy, much like how a heavy object creates depressions in the fabric of a stretched rubber sheet. If such structures were to exist, they would require exotic forms of matter with negative energy density, a substance that has never been observed or created in any laboratory setting, yet remains theoretically possible within the framework of quantum mechanics. What makes wormholes particularly intriguing is how they have transitioned from purely mathematical curiosities into legitimate subjects of serious scientific inquiry and research, despite the profound technical obstacles and the absence of any empirical evidence for their actual existence. This persistence speaks to the peculiar nature of theoretical physics itself, where mathematical elegance and logical consistency within established frameworks can grant legitimacy to ideas that may never manifest in observable reality, and where the tantalizing possibility that such structures might exist somewhere in the cosmos continues to captivate both professional physicists and the broader human imagination with visions of cosmic highways and pathways through spacetime. Recent theoretical work has explored whether traversable wormholes might be stabilized through configurations of dark energy or quantum effects near black hole horizons, though the energy requirements would dwarf anything humanity could feasibly harness. Ultimately, wormholes remain a humbling reminder of the vast gap between mathematical possibility and physical reality, embodying both the power and the limitations of our current understanding of the universe. Yet even this humbling recognition has not dimmed the enthusiasm of researchers who continue to probe the mathematical structure of general relativity for clues about whether nature might exploit such pathways. Understanding that the history of physics is replete with phenomena once deemed impossible that later proved not merely real but fundamental to our understanding of the cosmos. In the depths of space, where gravity reaches its most extreme expression, something peculiar happens at the very edge of a black hole's event horizon, a boundary from which nothing, not even light itself, is supposed to escape. and yet Stephen Hawking theorized in 1974 that black holes are not entirely black, but instead emit a faint radiation born from quantum fluctuations in the fabric of spacetime itself. The mechanism behind this phenomenon involves the strange dance of virtual particle pairs that continuously pop in and out of existence near the event horizon, a quantum process so fundamental to the universe that it occurs everywhere. Yet only near the immense gravitational field of a black hole does something remarkable happen. When these particle pairs appear just at the boundary of the event horizon, the gravitational tidal forces are so powerful that they can separate these twin particles before they have a chance to annihilate each other. And if one particle falls beyond the event horizon while its partner escapes into space, the escaping particle becomes real radiation while the other contributes negative energy that causes the black hole to gradually lose mass. This process means that black holes, those cosmic objects that seem to represent the ultimate triumph of gravity, are actually slowly evaporating, radiating away their substance into the universe bit by bit across timescales that dwarf the current age of the cosmos itself. The profound mystery embedded within Hawking radiation lies in how it defies our intuitive understanding of black holes as absolute prisons of gravity. Yet the mathematics of quantum mechanics and general relativity, when carefully combined, reveal this truth with remarkable elegance and precision. We have come to accept this strange reality as simply another feature of the quantum universe, another reminder that the cosmos operates according to principles far stranger than our everyday experience would suggest. And in doing so, we have normalized the idea that even the most impenetrable objects in the universe have an expiration date, that entropy and time claim dominion over all things, including the very concept of infinite gravitational collapse. Yet perhaps the most humbling aspect of this discovery is that it reveals black holes are not merely destructive agents, but are subject to the same thermodynamic laws that govern all matter and energy in the universe, suggesting that even the darkest corners of spacetime are woven into the grand tapestry of cosmic order and decay. This insight has transformed how we think about black holes themselves, from objects of pure destruction to thermodynamic systems with temperature, entropy, and a finite lifespan, and it has opened profound questions about what happens to the information that falls into a black hole, whether it is truly lost forever or somehow encoded in the radiation that escapes, a puzzle that remains one of the deepest unsolved mysteries in theoretical physics. Deep within the theoretical framework of black hole physics lies a paradox that has troubled physicists for decades, a contradiction so profound that it suggests something fundamental about our understanding of reality itself may be wrong. When an object falls into a black hole, quantum mechanics tells us that information about that object must be preserved somewhere in the universe. Yet general relativity insists that once anything crosses the event horizon, it vanishes from our observable reality forever, lost to the singularity within. This is the information paradox, and it led physicist Juan Maldacena and others to propose something called the Firewall hypothesis, which suggests that the event horizon of a black hole is not the gentle, unremarkable boundary that Einstein's equations initially suggested, but rather an extraordinarily violent barrier of energy that would incinerate anything attempting to cross it. The firewall paradox emerges from the collision of three principles that each seem individually sound, yet together appear mutually exclusive. Quantum mechanics demands that information cannot be destroyed, general relativity demands that the event horizon presents no special hazard to a freely falling observer, and black hole thermodynamics demands that black holes must eventually evaporate through Hawking radiation, carrying away information encoded in the properties of the radiation. When you attempt to honor all three principles simultaneously, you discover that at least one of them must give way, and yet physicists cannot agree on which one, if any, should be abandoned or modified. The firewall paradox persists in theoretical physics not because it has been solved, but because each proposed solution creates new problems elsewhere in the theoretical landscape. Some physicists argue that information must somehow be preserved in the radiation itself through mechanisms we do not yet understand, while others suggest that perhaps quantum mechanics itself must be revised at extreme scales, or that general relativity breaks down in ways we have not yet discovered. What makes this paradox particularly fascinating is that it remains entirely inaccessible to direct observation or experimentation, existing only in the realm of mathematical contradiction and theoretical consistency. Yet physicists continue to treat it as one of the most pressing problems in fundamental physics, a mystery that hints at deeper truths about the nature of information, spacetime, and reality itself. The firewall paradox thus stands as a monument to the limits of our current knowledge, a place where the three pillars of modern physics crack under the weight of their own contradictions, reminding us that even our most successful theories may be incomplete approximations of a deeper reality we have yet to comprehend. Perhaps the deepest lesson of the firewall paradox is that it reveals the boundaries of human knowledge not as fixed walls, but as dynamic frontiers where our most powerful theories converge and conflict, suggesting that future breakthroughs in physics may require entirely new conceptual frameworks that transcend our current categories of thought altogether. Deep within the theoretical foundations of modern physics lies a concept so profoundly counterintuitive that it challenges our most fundamental understanding of reality itself, suggesting that the universe we perceive as a three-dimensional space might actually be nothing more than a two-dimensional projection encoded on a distant boundary, much like a hologram created from light bouncing off a reflective surface. This idea emerged from the work of physicist Juan Maldacena in the 1990s, who discovered a mathematical relationship suggesting that a gravitational theory existing in a higher dimensional space could be completely equivalent to a quantum field theory existing on its lower dimensional boundary, implying that all the information contained within a volume of space might be stored entirely on its surface rather than throughout its interior. The mechanism behind this principle rests on the observation that the maximum information that can be contained in any region of space appears to be proportional to its surface area rather than its volume, a discovery that emerged from studying black holes and their entropy, fundamentally challenging the intuition that larger spaces should contain proportionally more information. When physicists calculated how much information a black hole could theoretically contain, they found that the amount was not determined by how much space existed inside the event horizon, but rather by the area of the event horizon itself, a relationship so unexpected that it suggested the three-dimensional reality we experience might be encoded like a holographic image on a two-dimensional surface at the edge of the observable universe. Yet despite the profound implications of this principle and its seeming contradiction to how we directly experience the world around us, it has become increasingly normalized within theoretical physics communities, accepted as a potentially legitimate description of reality without the widespread philosophical crisis or public concern one might expect such a revelation to generate. The holographic principle persists in academic discourse and research funding as scientists continue to develop its mathematical frameworks and search for observational evidence, perhaps because our minds have grown accustomed to accepting increasingly abstract and counterintuitive truths about the cosmos, or because the principle remains so removed from everyday human experience that it fails to trigger the same existential questioning that might accompany other paradigm-shifting discoveries about the nature of consciousness or our place in the universe. Yet if the holographic principle proves correct, it would mean that every conversation we have, every memory we form, and every moment of consciousness we experience is ultimately a lower dimensional shadow of information encoded on some cosmic boundary we may never directly observe, suggesting that the deepest nature of reality operates according to principles so alien to our evolved intuitions that we may require entirely new frameworks of thought to truly comprehend what existence fundamentally is. In the depths of theoretical physics lies one of the most unsettling propositions ever conceived by the human mind: the idea that the very fabric of reality itself, the quantum vacuum that permeates all of existence, might not be in its lowest possible energy state. This concept, known as vacuum decay, suggests that our universe could be fundamentally unstable, existing in what physicists call a false vacuum, a precarious equilibrium that could spontaneously collapse into a lower energy state without warning or precedent. The mechanism behind this catastrophic possibility emerges from quantum field theory, which describes how fundamental particles and forces interact at the smallest scales of reality, revealing that energy fields can exist in multiple states, much like a ball resting on a hill rather than at the bottom of a valley. If our universe's quantum vacuum were indeed in such a metastable state, then through the probabilistic nature of quantum mechanics, it could spontaneously transition to a true vacuum state, releasing enormous amounts of energy and fundamentally altering the physical constants that govern all matter and forces. Such an event would manifest as a bubble of true vacuum expanding outward at the speed of light, an expanding sphere of absolute transformation that would sweep across the cosmos, obliterating everything within it and replacing the fundamental laws of physics themselves with new and potentially hostile parameters. The psychological weight of contemplating vacuum decay stems from its complete indifference to human awareness or intervention, the recognition that existence itself may harbor an existential instability built into its foundation, an inherent flaw in the cosmic architecture that no technology or knowledge could prevent or escape. What makes vacuum decay particularly troubling is that we cannot observe whether our vacuum is stable or metastable from our current position within it. Much like a creature confined to a single room cannot determine whether the walls surrounding it are permanent or temporary, and despite decades of theoretical work and experimental searches for evidence of quantum instability, we continue our daily existence in a kind of profound ignorance. Neither certain our reality will persist, nor capable of doing anything should we discover it will not. This normalization of existential uncertainty, this quiet acceptance that our universe might be fundamentally unstable, reflects humanity's remarkable capacity to compartmentalize cosmic dread, to intellectually acknowledge the possibility of absolute annihilation while simultaneously continuing to plan for futures and construct meaning within a framework we understand to be potentially temporary. A psychological adaptation that allows consciousness to persist in full awareness of its possible illusory permanence. Imagine the universe as we know it existing in a state of precarious balance, suspended in what physicists call a false vacuum, a condition where all of matter and energy occupy what appears to be a stable ground state, but is actually something far more unstable and temporary than we typically assume. According to this theory, the Higgs field that permeates all of existence might not actually be at its lowest possible energy state, but rather trapped in a local minimum, like a ball resting in a shallow valley when an infinitely deeper valley exists just beyond the horizon. The universe could theoretically undergo quantum tunneling, a phenomenon where the fabric of reality itself spontaneously transitions to a lower energy state through what seems to us like random chance. And when this transition occurs, it would manifest as an expanding bubble of true vacuum that propagates outward at the speed of light, destroying all physical laws and structures in its path as it fundamentally rewrites the constants that govern existence. This concept emerged from quantum mechanics and string theory calculations, suggesting that the universe's current state represents just one possibility among countless configurations, each with different physical laws and constants, and the deeper truth of reality might be defined by these alternative vacuous states hidden in the mathematical structure of space itself. The psychological mechanism by which scientists and physicists engage with this theory involves accepting that the laws we observe as eternal and unchangeable might be mere accidents of our particular region of space, and that reality as we perceive it could be erased instantaneously by forces beyond observation or prevention, which creates a peculiar cognitive tension between our need for cosmic permanence and the apparent fragility revealed by theoretical physics. What makes false vacuum theory particularly unsettling is that it has persisted as a legitimate field of inquiry despite its seeming unfalsifiability, and the fact that we have no way to detect whether we currently exist in a false vacuum, nor any method to predict or prevent such a catastrophic event. Yet physicists continue to refine and explore it with serious mathematical rigor, treating the ultimate cosmic uncertainty not as philosophy, but as genuine physics worthy of investigation. Some researchers have even speculated that previous universes might have undergone this transition, each catastrophic collapse seeding the conditions for new cosmic inflation, suggesting that our own existence might be the aftermath of such an event rather than its harbinger, a possibility that transforms false vacuum theory from mere speculation about our future into a potential explanation for our mysterious origins. In the first fraction of a second after the Big Bang, something extraordinary happened to our universe that defies our everyday intuition about how space and time should behave. According to the inflationary theory proposed by Alan Guth and Andre Linde in the 1980s, the universe underwent an incomprehensibly rapid expansion during which it doubled in size not once or twice, but perhaps 80 times over in a period so brief that light itself could not traverse the growing distance. During this epoch called cosmic inflation, space itself expanded faster than the speed of light, stretching the fabric of reality in all directions simultaneously with an acceleration that seems to violate everything we thought we understood about relativity and the cosmic speed limit. The universe inflated from something smaller than a proton to perhaps the size of a grapefruit in the tiniest fraction of a second, and this explosive growth smoothed out the irregularities in the early universe while simultaneously stretching quantum fluctuations to cosmic scales. The mechanism that drove this inflation remains mysterious, theorized to involve a hypothetical field called the inflaton field, whose energy density pushed space outward with relentless force. Yet we cannot directly observe this field or detect it in our experiments. What makes cosmic inflation particularly intriguing is that it resolves several profound cosmological puzzles that otherwise seem inexplicable, such as why the universe appears so homogeneous and flat and isotropic when there seems no reason it should be. Yet despite solving these mysteries, inflation itself introduces new mysteries that are perhaps even more perplexing, because we have no confirmed evidence that it actually occurred, and the theory requires the existence of particles and fields that exist beyond our ability to detect them directly. We have accepted cosmic inflation as the leading explanation for our universe's origin because it makes predictions that align with observations from the cosmic microwave background radiation. Yet we simultaneously acknowledge that the theory may be incomplete or even incorrect, and that the mechanisms driving inflation remain hidden from our instruments and perhaps forever beyond our understanding. The inflationary paradigm has spawned competing models: chaotic inflation, eternal inflation, slow-roll inflation, each proposing subtly different mechanisms and timescales, yet all sharing the core conviction that an early universe expansion phase explains observations we would otherwise struggle to comprehend. In this way, cosmic inflation represents both a triumph of theoretical physics in explaining the universe's large-scale structure and a humbling reminder of how much remains unknown about the fundamental nature of existence itself. Perhaps most humbling of all is the possibility that inflation itself may be merely one chapter in a far grander cosmic story, with the Big Bang and inflation themselves emerging from physics we have yet to discover, suggesting that our current understanding of the universe's origin may someday seem as incomplete as pre-inflationary cosmology appears to us today. Imagine standing at the edge of a vast conceptual precipice, where the singular universe we have always understood to be our reality fractures into infinite parallel versions of itself, each one containing different outcomes of every possible event that could ever occur, and in this framework known as multiverse theory. Every quantum decision point spawns new universes branching eternally outward, like an incomprehensibly vast cosmic tree where you exist in countless variations, simultaneously making different choices in each one. The scientific foundation for this concept emerges from several legitimate areas of physics, particularly from quantum mechanics, where the many worlds interpretation suggests that when a quantum particle exists in superposition until observed, the act of measurement does not collapse it into one state, but rather splits reality itself into multiple branches, where each possible outcome is realized in a separate universe. Additional theoretical support comes from cosmic inflation theory, which proposes that the Big Bang did not occur only once, but continues eternally in some regions of space while other regions cease expanding, creating bubbles of universe throughout an infinite multiverse landscape. String theory further contributes to this idea by suggesting that our universe is merely one of up to 10 to the 500th power possible universes, each with different fundamental constants and physical laws. The psychological mechanism driving our acceptance of multiverse theory operates through several interconnected processes. First, it provides a profound sense of existential comfort by suggesting that all possibilities are realized somewhere, eliminating the anxiety of unmade choices and unexplored paths. Second, it appeals to our pattern recognition instincts by offering a mathematically elegant framework that extends principles we already accept in quantum mechanics. And third, it positions us within a grander narrative where our significance is both diminished and multiplied simultaneously, creating a paradoxically soothing intellectual vertigo. Despite the profound conceptual appeal of multiverse theory, it remains fundamentally untestable through any practical means, as parallel universes exist beyond our observable horizon and may never transmit detectable signals across the dimensional boundaries that separate them. Yet we have somehow normalized this unfalsifiable speculation as serious scientific inquiry worthy of considerable intellectual and financial investment. Speaking of countless universes with the same casual certainty we once reserved for describing the single cosmos we can actually observe and study. This inversion of epistemic standards, granting theoretical legitimacy to the untestable while demanding empirical proof for the observable, reveals how our hunger for cosmic narratives can subtly override the rigorous methodology that science purports to protect, allowing us to construct increasingly elaborate theoretical architectures upon foundations of pure speculation simply because the mathematics happens to be elegant. Imagine the cosmos not as a single unified reality stretching infinitely in all directions, but rather as an endlessly expanding foam of disconnected universes, each one isolated within its own bubble, separated from all others by impenetrable walls of spacetime that no light, no matter, and no information could ever cross. This is the concept of bubble universes, a theoretical framework emerging from our understanding of cosmic inflation and the mathematics of quantum mechanics applied to the very fabric of existence itself. According to this model, in the moments following the Big Bang, space underwent exponential expansion, but this expansion did not occur uniformly or smoothly across all regions. Instead, certain areas of spacetime experienced violent, rapid inflation, while others cooled and crystallized into stable universes with their own distinct physical laws, fundamental constants, and dimensional structures. Each bubble universe represents a pocket of reality where inflation eventually halted, creating a pocket of order within the chaos of expanding spacetime. What makes this concept particularly profound is the implication that countless universes exist simultaneously, each with potentially different rules governing how particles interact, how forces operate, and what forms of matter and energy can exist within their boundaries. The mechanism driving this conception stems from the inflationary theory developed in the 1980s, which proposed that the early universe underwent a period of exponential growth driven by a quantum field called the inflaton field. When physicists examined the quantum fluctuations inherent in this field at the smallest scales, they discovered that these fluctuations could cause different regions of space to reach different vacuum states, essentially different ground energy levels that define the physical properties of that region. Some areas might settle into a state where the strong nuclear force behaves one way, while neighboring bubbles might have completely different strengths for fundamental forces, resulting in entirely alien periodic tables of elements and physics that we cannot observe or predict. This framework attempts to address profound questions about why our universe has the particular constants and laws it does, suggesting that we simply inhabit one bubble among an infinite ensemble where all possible configurations exist somewhere. Yet despite having no observational evidence and no conceivable way to detect other bubbles given the insurmountable barrier of expanding space between them, this idea has become deeply embedded in theoretical physics discourse, discussed as though it represents genuine physics rather than elaborate mathematical speculation. The persistence of bubble universe theory reveals how the scientific community has normalized a form of thinking that transcends empirical falsifiability, where mathematical elegance and theoretical consistency have become sufficient justification for exploring ideas that exist permanently beyond the reach of experimental verification or observation. Imagine standing in a vast, empty room where nothing should exist, yet something does. This is the fundamental paradox that physicists have grappled with for over a century, a problem so profound that it touches the very nature of reality itself. The cosmological constant problem emerges from a peculiar disagreement between what theory predicts and what observation reveals about the energy density of empty space, often referred to as dark energy or vacuum energy. When physicists attempt to calculate the energy that should naturally exist in the quantum vacuum, that supposedly empty space between all particles where virtual particles briefly flicker in and out of existence, their mathematics produces a number so astronomically large that it should have torn the universe apart within fractions of a second after the Big Bang, yet clearly it did not. The observed density of this vacuum energy, inferred from measurements of how the universe expands, is extraordinarily small, perhaps 120 orders of magnitude smaller than the theoretical prediction. This is equivalent to predicting that a single grain of sand would weigh as much as Mount Everest, or that a single atom would contain the mass of a galaxy. The mechanism underlying this problem lies in the interaction between quantum field theory and general relativity, two pillars of modern physics that refuse to speak the same language. Quantum field theory insists that empty space seethes with energy fluctuations, while general relativity demands that any energy present in space must curve spacetime, yet the observed curvature of space from this vacuum energy is vanishingly small. Scientists have proposed numerous solutions, from the idea that some unknown mechanism precisely cancels most of the vacuum energy to the concept of multiple universes, where we inhabit one of the rare regions with low vacuum density. Yet despite decades of theoretical work and increasingly precise observations, the problem persists unresolved, a glaring reminder that our fundamental understanding of the cosmos remains incomplete and that nature guards her deepest secrets with remarkable stubbornness. This incompleteness is particularly humbling because the cosmological constant problem represents not merely a gap in our knowledge, but potentially a fundamental limitation in how we reconcile the quantum and gravitational realms, suggesting that the next great revolution in physics may require us to abandon or radically reimagine one of our most cherished theoretical frameworks. Perhaps most tantalizingly, this problem may ultimately reveal that vacuum energy is not truly empty at all, but rather a manifestation of physics operating at scales so minute, or in dimensions, so hidden that our current instruments and theories simply lack the sophistication to perceive them directly. What makes this mystery even more intriguing is that dark energy now comprises roughly 70% of the universe's total energy content, meaning we have named and measured something we fundamentally do not understand. A situation reminiscent of ancient astronomers marking unknown celestial objects as "here be dragons" on their maps. Consider the profound paradox that sits at the very heart of modern physics. The vacuum of space, that seemingly empty void between galaxies and atoms, is not empty at all, but rather seethes with an invisible energy so vast and mysterious that it challenges our fundamental understanding of reality itself. According to quantum field theory, the vacuum is never truly empty because the uncertainty principle demands that particles and antiparticles constantly blink in and out of existence at scales too small for us to directly observe, creating what physicists call virtual particles that exist for impossibly brief moments before annihilating one another. Yet their presence leaves measurable effects in the fabric of spacetime itself. This vacuum energy, also known as dark energy or the cosmological constant, appears to permeate every cubic centimeter of the universe with a density so peculiar that when calculated using our best theoretical predictions, the answer comes out approximately 120 orders of magnitude larger than what we actually observe in reality, a discrepancy so absurdly vast that it represents perhaps the most profound failure of prediction in the history of science. The mechanism behind this mystery involves the fact that when physicists attempt to calculate the energy of quantum fluctuations in the vacuum, they sum up contributions from all possible virtual particles at all possible energies, and without some form of cutoff or modification to the theory, this sum grows infinitely large, producing what is called the cosmological constant problem. A mathematical catastrophe that suggests our current theoretical framework is fundamentally incomplete, or that we are missing some crucial physical principle that governs the behavior of spacetime at the smallest scales. What makes this particularly unsettling is that despite this enormous theoretical prediction being catastrophically wrong, the universe continues to behave as though vacuum energy actually exists and is driving the accelerating expansion we observe through our telescopes, meaning that empty space itself possesses properties and effects that our equations cannot adequately explain. Yet we have nonetheless incorporated this mysterious force into our models because the observational evidence for its existence is undeniable, creating a situation where modern cosmology rests upon a foundation of profound ignorance dressed up in mathematical language. The discovery that the universe's expansion is accelerating, inferred from observations of distant supernovae in the late 1990s, only deepened this enigma by providing concrete evidence that something real fills the cosmos and pushes galaxies apart. Yet we cannot identify what this something fundamentally is, leaving us in the peculiar position of having mapped its gravitational effects with precision while remaining almost entirely ignorant of its nature. Consider two particles that have interacted with one another in such a way that their quantum states become fundamentally linked, creating what physicists call an entangled pair, and imagine that these particles are then separated by vast distances, perhaps placed on opposite sides of the observable universe with billions of light-years stretching between them. And yet when you measure a property of one particle, such as its spin or polarization, the other particle instantaneously adopts a corresponding state that perfectly correlates with the first measurement, regardless of the distance separating them, as if they remain connected by an invisible thread that transmits information faster than the speed of light itself, which according to Einstein's theory of relativity should be impossible. And yet this phenomenon has been experimentally verified countless times in laboratories around the world. With researchers conducting Bell tests and other rigorous experiments that consistently demonstrate this non-local correlation between entangled particles. The mechanism underlying this apparent paradox rests upon a profound misunderstanding of what entanglement actually is and what it means for particles to share a quantum state. For the correlation is not caused by some hidden signal traveling between the particles, but rather emerges from the fact that entangled particles do not possess definite individual properties until they are measured, instead existing in a state of superposition where all possible outcomes remain equally probable. And when you measure one particle, you collapse that shared quantum state, instantly determining not only the measured particle's properties, but also the properties of its distant partner, since they were never truly separate entities with independent states to begin with. What allows this phenomenon to persist within our understanding of physics is our gradual acceptance that the quantum realm operates according to fundamentally different rules than the classical world of everyday experience, where separation implies independence and distance implies isolation. Yet quantum mechanics reveals that reality at its smallest scales does not respect these intuitive assumptions, and we have learned to normalize this strangeness by building it into our equations, our theories, and our experimental protocols, treating entanglement not as an impossible violation of physical law, but rather as a natural consequence of quantum mechanics itself. And consequently, we have begun to explore practical applications of this phenomenon in quantum computing and quantum cryptography, transforming what initially seemed like a conceptual paradox into an operational resource. Demonstrating how thoroughly we have come to accept that the deepest layers of reality operate in ways that defy our everyday logic. Yet even as we harness entanglement's power, we remain humbled by how much we still do not understand about the nature of reality itself, recognizing that each technological breakthrough only deepens the mystery of why the universe permits such profound connections to exist across the void of space. Consider two particles that have been entangled in a quantum laboratory, their properties mysteriously linked through the fundamental fabric of reality itself. And then imagine these particles being separated across vast distances, perhaps light-years apart, with one particle placed in an observatory on Earth and its twin sent toward the edge of our observable universe. When a physicist measures a property of one particle, such as its spin or polarization, something extraordinary occurs. The distant particle instantaneously responds and aligns itself with a corresponding property, as though some invisible signal traveled between them faster than light could possibly travel, defying everything we understand about the cosmic speed limit that Einstein established over a century ago. This phenomenon, which Einstein himself famously called spooky action at a distance, troubled the greatest physicist of our time, because it seemed to violate the fundamental principle that nothing can travel faster than light. Yet experiments have repeatedly confirmed that this quantum correlation is absolutely real and measurable. The mechanism operating beneath this mystery appears to involve the nature of quantum superposition itself, where particles exist in multiple states simultaneously until observed, and the correlation between entangled particles means they share a single quantum state described by mathematics. So when one is measured, the shared state collapses for both particles instantly regardless of the distance separating them. Not because information travels between them, but because they were never truly separate in the quantum sense at all. What makes this persistence so remarkable is that despite decades of experimental verification and theoretical refinement, we have somehow normalized the idea that reality itself operates in ways that contradict our deepest intuitions about locality and separability, accepting that the universe permits correlations more fundamental than any physical signal, and we continue our daily lives in a cosmos that behaves in ways that would have seemed like pure magic just generations ago. Yet now we treat this weirdness as established fact. Perhaps the deepest irony is that this spooky phenomenon, once considered a threat to our understanding of physics, has become the foundation for emerging technologies like quantum computing and quantum cryptography, transforming what Einstein saw as a crisis into a resource, suggesting that the universe's most counterintuitive features may ultimately prove to be its most powerful tools. In laboratories today, scientists are already harnessing entanglement to build quantum networks that could revolutionize secure communication and computational power, turning Einstein's philosophical objection into practical innovation, while simultaneously deepening our humbling realization that the universe operates according to principles far stranger and more elegant than our classical intuitions ever allowed us to imagine. Deep within the universe, galaxies engage in a process so violent and transformative that it fundamentally reshapes their structure and identity, a phenomenon astronomers have termed galactic cannibalism, which occurs when a larger galaxy gravitationally consumes a smaller neighboring galaxy through a process that unfolds across millions of years as tidal forces gradually pull the smaller galaxy apart, stretching it like taffy until its stars, gas, and dark matter merge completely with the host galaxy, leaving behind only the absorbed material now incorporated into the larger system. This process begins subtly, with the gravitational influence of the larger galaxy creating tidal distortions in the smaller one, causing its outer stars to drift away and its structure to become increasingly warped and distorted until eventually the smaller galaxy loses all coherence and its remaining stars fall inward toward the center of the larger galaxy, creating temporary rings and shells of stellar material that slowly settle into the new galactic structure over billions of years. The mechanism behind this cosmic merger lies in the fundamental nature of gravity itself, where mass curves spacetime and creates attractive forces that become overwhelming when two massive objects draw sufficiently close. And when galaxies collide or pass near each other, the mathematical inevitability of gravitational attraction means that the smaller body cannot escape the gravitational well of the larger one, leading to an inexorable process of consumption that transforms both galaxies involved while the larger galaxy grows substantially in mass and the smaller one ceases to exist as a distinct entity. What proves remarkable about galactic cannibalism is how thoroughly normalized it has become in our understanding of cosmic evolution. For astronomers now recognize this process as a primary mechanism through which galaxies grow and evolve, with evidence suggesting that our own Milky Way has consumed dozens of smaller galaxies throughout its history and will eventually merge completely with the Andromeda Galaxy in approximately 4.5 billion years. Yet despite the catastrophic and violent nature of this process, we discuss it with calm scientific detachment as merely another chapter in the inevitable story of cosmic development, treating the obliteration and absorption of entire galaxies as a routine and expected outcome rather than as something that should strike us with existential wonder at the sheer scale and power of gravitational forces at work throughout the universe. Yet within this framework of cosmic consumption lies a paradox. The very process that destroys individual galaxies may also be essential to the formation of the massive elliptical galaxies we observe today, suggesting that galactic cannibalism, for all its violence, represents not merely destruction but transformation, a recycling of cosmic material into ever larger structures that continue to shape the evolving universe across incomprehensible spans of time. Consider the vast expanse of space that stretches between galaxies, a realm so incomprehensibly distant that light itself takes millions of years to traverse the void. And within this cosmic ocean exists a phenomenon that challenges our fundamental understanding of stellar physics and the very nature of gravitational interaction across the universe. These intergalactic stars are solitary stellar bodies that have been ejected from their parent galaxies through mechanisms we are only beginning to comprehend, torn away from the gravitational embrace of their original homes by the violent collisions of black holes, the chaotic dynamics of multi-star systems, or the catastrophic mergers of entire galactic structures themselves. What makes this phenomenon particularly perplexing is that these orphan stars continue to exist and move through intergalactic space with remarkable persistence, traveling through an environment so sparse that they encounter almost nothing, maintaining their nuclear fusion processes and their fundamental stellar properties despite being isolated in a region where they should theoretically be unable to interact with any meaningful source of material or energy. The psychological mechanism by which we accept this reality operates through compartmentalization, allowing us to acknowledge these intergalactic wanderers as genuine astrophysical objects, while simultaneously maintaining our conventional models of stellar formation and galactic stability. essentially creating a category of cosmic anomaly that we discuss in scientific literature, yet rarely integrate into our broader conceptual frameworks of how the universe should logically function. We have normalized the existence of these stellar exiles by simply classifying them as ejected stars, by assigning them names and trajectories, by calculating their velocities and estimating their ages, thereby transforming a deeply unsettling violation of our expectations into a mere cataloging exercise, another footnote in the expanding ledger of cosmic phenomena that defies intuitive explanation yet remains persistently real. Yet perhaps this normalization through nomenclature reveals something profound about human cognition itself, our capacity to transmute wonder into taxonomy, to render the extraordinary mundane through the simple act of explanation, and in doing so, to maintain the illusion that we have truly understood what we have merely named. And yet, when we observe these solitary stars through our telescopes, detecting their faint light as it arrives after traveling unimaginable distances, reconstructing their histories from spectroscopic data, we are reminded that naming is not mere obfuscation, but rather an act of connection, a way of acknowledging that even in the vast indifference of the cosmos, individual stellar bodies persist, wander, and continue their silent fusion across the infinite dark, refusing to be erased by their exile from home. In the deep expanse of our galaxy, there exist certain stars that move through space at velocities so extraordinary that they seem to violate our fundamental understanding of how objects should behave within gravitational systems, traveling at speeds exceeding 1,000 kilometers per second, which is fast enough to escape the gravitational grip of the Milky Way itself and venture into the intergalactic void. These hypervelocity stars were first theoretically predicted and later observationally confirmed, and they represent one of the most perplexing phenomena in astrophysics, because their existence demands that we reconsider the mechanisms by which stars acquire such tremendous kinetic energy. The prevailing explanation centers on a gravitational interaction of extraordinary violence occurring near supermassive black holes, wherein a binary star system ventures too close to the event horizon, and the immense tidal forces tear the system apart, flinging one star outward at velocities that seem almost incomprehensibly high, while the other plunges into oblivion. Yet this mechanism alone does not fully account for all observed hypervelocity stars, suggesting that other ejection processes remain poorly understood. What makes this phenomenon particularly unsettling to contemplate is the realization that these stars were once ordinary residents of galactic neighborhoods, quietly orbiting in stellar associations or clusters, and then through what might be described as an astronomical catastrophe or improbable cosmic accident, they were violently cast adrift into a solitary journey through darkness. The psychological impact of understanding hypervelocity stars stems from recognizing that even objects as massive as stars are ultimately vulnerable to forces so powerful that they can be ejected from entire galaxies, that stability is illusory, and that the universe contains mechanisms of violence and chaos operating at scales that humble our comprehension. Yet despite these troubling implications about the fundamental instability of cosmic systems, we have normalized the existence of hypervelocity stars into our scientific frameworks, cataloging them methodically and discussing their properties with detached analytical precision, transforming something genuinely unsettling about the universe into merely another entry in our astronomical surveys, another data point in our understanding of galactic dynamics. Perhaps this normalization itself represents a peculiar human strategy for coping with cosmic indifference. By rendering the extraordinary routine through scientific nomenclature and measurement, we create a psychological distance from the vertiginous reality that the universe operates according to principles fundamentally indifferent to our sense of stability and permanence. In this way, hypervelocity stars become not merely objects of scientific study, but mirrors reflecting our own condition, inhabitants of a cosmos where the ground beneath our feet, metaphorically speaking, offers no ultimate guarantee of permanence, and where even the grandest celestial bodies can be reduced to wanderers cast into the void by forces indifferent to their fate. In the vast expanse of our galaxy, there exist stars that move through space at velocities so extraordinary that they seem to violate our expectations of how celestial bodies should behave, and these stellar fugitives are known as runaway stars, objects that travel at speeds between 30 and 200 kilometers per second, far exceeding the typical orbital velocities of their stellar siblings, and creating a phenomenon that challenges our understanding of stellar dynamics and gravitational interaction. These runaway stars achieve their remarkable velocities through mechanisms that involve the violent disruption of binary star systems, where a massive star completes its life cycle by exploding as a supernova in an asymmetrical manner, an explosion so unbalanced that it imparts a sudden and tremendous kick to its companion star, sending it hurtling through the galactic plane like a cosmic bullet fired from an invisible gun. The physics behind this acceleration is rooted in the conservation of momentum and the anisotropic nature of supernova explosions, where matter is not ejected uniformly in all directions, but instead streams preferentially in certain directions due to the rapid rotation of the progenitor star or magnetic field interactions, creating a recoil effect that propels the surviving companion star at velocities the universe rarely grants to such massive objects. What makes runaway stars particularly fascinating to contemplate is how they continue their solitary journeys through space for billions of years, completely divorced from any stellar companion or gravitational anchor, yet still bound to the galaxy by its immense gravitational field, traveling through the darkness between stars in a state of permanent exile from the stellar nurseries where they were born. We observe these runaway stars scattered throughout our galaxy and beyond, their existence confirmed through careful measurement of their proper motions and radial velocities. Yet they remain objects of profound mystery because the exact mechanisms that produce them are not entirely understood, and scientists continue to debate whether supernova kicks alone can account for all observed runaway stars or whether other processes, such as dynamical encounters in crowded star clusters or interactions involving three or more stars, might also contribute substantially to their creation. The persistence of runaway stars in our universe, despite their chaotic origins, suggests that stellar systems are far more dynamic and violent than once thought, and their trajectories trace invisible paths through the cosmos that will eventually carry them beyond the gravitational boundaries of our galaxy, where they will drift alone into the intergalactic void for all eternity. Among the most celebrated examples is Zeta Ophiuchi, a massive blue star moving through space at 90 kilometers per second, leaving behind a visible bow shock as it plows through the interstellar medium, a cosmic wake that illuminates the violence of its ejection and serves as a testament to the turbulent origins that define these wandering stellar exiles. Consider the region of space surrounding our own galactic neighborhood, a vast expanse that astronomers have come to call the local void, and contemplate what this designation truly means for our understanding of the cosmos at the largest scales. The local void is a region spanning roughly 150 million light-years across, centered approximately 90 million light-years away from our Milky Way galaxy, characterized by an almost complete absence of matter, a vast bubble of relative emptiness where galaxies are extraordinarily sparse compared to the cosmic average, where the density of galaxies drops to perhaps 1/10 or even 1/100th of what we observe in other regions of the universe, creating an area so underpopulated that it challenges our fundamental assumptions about how matter should be distributed throughout space. What makes this phenomenon particularly perplexing is that the local void appears to exert a measurable gravitational effect on our own galaxy and its surrounding cluster, pulling us away from the densely populated regions beyond it, suggesting that the absence of matter itself has consequences equivalent to a repulsive force, which seems to contradict the basic principle that gravity only attracts and cannot push. The psychological mechanism underlying our difficulty in understanding voids relates to our intuitive expectation that the universe should present a relatively uniform distribution of matter on the largest scales, a concept known as the cosmological principle, which posits that on sufficiently large scales, the universe appears essentially the same everywhere. Yet these massive underdensities undermine this comforting notion by revealing a cosmos far more clumpy and heterogeneous than we might prefer to imagine. We have normalized this anomaly by incorporating voids into our standard cosmological models and treating them as natural consequences of gravitational collapse and the formation of large-scale structure. Yet the fundamental mystery persists regarding how such enormous regions of emptiness formed and maintained themselves across billions of years, and whether the gravitational repulsion from surrounding density differences truly accounts for their observed influence on galactic motion. Recent observations of the local void's influence on the cosmic microwave background radiation and the peculiar velocities of nearby galaxy clusters suggest that understanding voids may be as crucial to mapping cosmic structure as understanding the overdense filaments and clusters themselves, fundamentally reframing voids from mere gaps in the universe to active participants in shaping the large-scale geometry that defines our place within it. This reorientation invites us to reconsider whether emptiness itself is a fundamental feature of cosmic architecture, as essential to the universe's structure as matter and energy, and to recognize that the local void may ultimately reveal as much about the cosmos's deep nature as the most luminous galaxies and densest clusters ever could. In the earliest moments after the Big Bang, approximately 13.8 billion years ago, the universe existed in a state of profound darkness, filled with neutral hydrogen atoms that absorbed nearly all light passing through them, creating what cosmologists refer to as the cosmic dark ages. Then, sometime between 100 million and 900 million years after the cosmic origin, something extraordinary occurred that fundamentally transformed the nature of reality itself. The universe became reionized, meaning that hydrogen atoms throughout space were stripped of their electrons by ultraviolet radiation, creating a transparent cosmos that allowed light to travel freely across vast distances for the first time. This transition from neutral to ionized hydrogen seems straightforward in principle, yet when astronomers and physicists examine the actual observational evidence and perform detailed calculations, they discover a profound discrepancy that challenges our understanding of stellar physics and the early universe's evolution. The mystery centers on a relatively simple question: where did all the ultraviolet radiation necessary to reionize the entire universe actually come from, and how was it produced in sufficient quantities to accomplish this cosmic transformation so rapidly? Current models suggest that young, massive stars within the first galaxies provided most of this ionizing radiation. Yet when researchers carefully count the number of stars that existed during this epoch and calculate how much ultraviolet light they could have emitted, the numbers persistently fall short of what would be required to reionize the universe within the observed timeframe. Additional sources of radiation remain theoretically possible, including active galactic nuclei powered by supermassive black holes, or perhaps exotic contributions from dark matter interactions or other yet unknown phenomena. But none of these supplementary mechanisms have been convincingly demonstrated to exist in the required quantities. What makes this mystery particularly fascinating is how it reveals the fundamental limitations of our current understanding despite our sophisticated telescopes and advanced computational models. We have mapped the large-scale structure of the universe, detected gravitational waves, and observed the cosmic microwave background radiation with extraordinary precision, yet we cannot fully explain how the universe transitioned from darkness into light. The reionization mystery persists not because the question is unanswerable, but because it exposes a genuine gap between observation and theory, a space where our models must inevitably evolve as new evidence emerges, and as our instruments grow more capable of peering into those ancient, distant epochs when the universe underwent one of its most dramatic transformations. In the beginning, roughly 13.8 billion years ago, the universe emerged from an incomprehensibly hot and dense state, expanding rapidly into existence with nothing but hydrogen and helium scattered throughout an almost perfectly uniform darkness. For nearly 300 million years, this cosmos remained largely dark and featureless, a period astronomers now call the cosmic dark ages, where no stars yet burned and no light pierced the primordial void except for the faint afterglow of creation itself. Then, in what must have been a profound cosmic turning point, gravity began its slow and inexorable work on tiny density fluctuations that had been imprinted into the fabric of matter itself, pulling hydrogen gas together into increasingly dense clumps until the pressure and temperature at the centers of these collapsing clouds became so intense that nuclear fusion ignited for the very first time. These first stars, born from the collapse of primordial gas clouds with no heavy elements whatsoever, would have been monumentally different from the stars we observe today, burning with extraordinary intensity and reaching masses hundreds of times greater than our own sun, their brief and violent existences lasting mere millions of years before exploding catastrophically as supernovae. The psychological weight of contemplating these first stars rests in the recognition that they represent the universe beginning to know itself, to generate light and structure and complexity from near total simplicity, yet they remain fundamentally unknowable to us in their specific details because their light has long since faded and been replaced by the generations of stars that followed. We observe their legacy only indirectly, through the heavy elements they created and scattered across the cosmos, through the subtle signatures they left in the universe's structure, through mathematical models and educated inferences that bridge the gap between what we can see and what must have been. And yet, despite the impossibility of direct observation and the vast gulf of time separating us from their birth, we speak of these first stars with the same certainty we speak of things we can measure directly. Having incorporated this profound unknowability so thoroughly into our understanding that we rarely pause to acknowledge the strange leap of faith required to assert anything definitive about their existence at all. Yet this leap of faith is perhaps justified, for the first stars left unmistakable fingerprints. The heavy elements forged in their cores, carbon, oxygen, iron, gold, are woven into every planet, every living thing, every atom of our own bodies, making us quite literally composed of stardust from an era we will never witness directly. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in the furnaces of those first stars and scattered across the cosmos by their violent deaths, meaning that when we study the first stars, we are ultimately studying the deep origins of ourselves. In the earliest moments following the Big Bang, when the universe was barely more than a few 100 million years old, there existed a generation of stars unlike anything we observe in the cosmos today. Massive celestial objects composed almost entirely of hydrogen and helium with virtually no heavier elements. No carbon, no oxygen, no iron, no metals of any kind, and these theoretical constructs are known to astronomers as population III stars, representing the very first generation of stellar bodies ever to ignite in the universe. The mechanism behind their formation rests on a peculiar asymmetry in cosmic history, for in those ancient epochs the universe contained none of the complex elements that would later seed planetary systems and eventually enable the emergence of life itself. And instead only the primordial gases ejected from the Big Bang existed in vast clouds that would gravitationally collapse under their own weight to form these first stars. We understand through calculations and theoretical models that these population III stars must have been extraordinarily massive, perhaps hundreds of times larger than our Sun, burning with such intense fury that their lives would have been brief, spanning mere millions of years rather than the billions of years our own star will endure. And when they finally exhausted their nuclear fuel and collapsed catastrophically, they would have exploded as supernovae of incomprehensible power, scattering the first heavy elements throughout space, and thereby seeding the universe with the chemical complexity necessary for subsequent generations of stars and planets to form. The paradox that persists in our contemplation of population III stars is that we have never directly observed a single one, despite their theoretical certainty. For by the time our telescopes could peer back through time to the epoch when they should have existed, their light has either been too faint to detect or too redshifted beyond our instrumental capabilities. And yet we accept their existence with considerable confidence, because the heavy elements we observe throughout the universe today can only have been created within stellar furnaces, meaning these primordial stars must have existed and must have lived and died in those earliest cosmic moments. And so we inhabit a universe whose history is forever shaped by phenomena we can only infer indirectly, building our understanding through mathematics and logic rather than direct observation. A humbling reminder that our knowledge extends only as far as our instruments and our theoretical frameworks allow us to perceive. Yet perhaps this limitation itself reveals something profound about the nature of scientific inquiry. That we are driven to understand not only what we can see, but what we can infer from the echoes of the past. And in studying the elemental abundance patterns found in the oldest known stars and in the cosmic microwave background radiation, we find corroborating evidence that these population III giants did indeed seed the cosmos with their dying breaths, transforming a universe of pure simplicity into one rich with possibility. When we observe the universe at its largest scales, mapping the distribution of galaxies across billions of light years, we encounter structures so vast and intricate that they challenge our fundamental understanding of how matter organizes itself under the influence of gravity alone. These structures are called galactic filaments, and they form the cosmic web that connects galaxies throughout space like an impossibly delicate lattice woven from the fabric of reality itself. These filaments are not random accumulations of matter, but rather represent the largest organized structures in the observable universe, extending for hundreds of millions of light years and containing thousands upon thousands of galaxies strung together in elongated, thread-like formations. The filaments define the boundaries of vast cosmic voids, regions of nearly empty space that dwarf anything we can conceive of on human scales, yet they themselves remain densely populated with matter and galaxies that follow these invisible highways through the darkness of space. What makes galactic filaments conceptually troubling is that according to our current models of structure formation in the universe, the sheer scale and rapid appearance of these filaments in cosmic history should not be possible within the timeframe that our universe has existed. Yet they clearly emerged and organized themselves far more quickly than gravitational attraction alone could account for. The mechanism we believe explains their existence involves the interplay between dark matter gravitational scaffolding and the initial density fluctuations from the early universe. Yet these mechanisms produce a universe that should appear far more uniform and homogeneous than what we actually observe. We have largely normalized this discrepancy by adjusting our models and invoking additional unknown properties of dark matter and dark energy, effectively accepting that our predictions do not match observations while simultaneously proceeding as though our theoretical framework remains fundamentally sound and reliable for understanding cosmic evolution and structure formation. Yet the filaments themselves continue to reveal their secrets through observation. The Sloan Great Wall, the Hercules-Corona Borealis Great Wall stretching nearly 10 billion light-years across space, and countless others demonstrate a universe far more structured and organized than our theoretical models suggest it should be, inviting us to consider whether the framework itself requires deeper revision rather than mere parameter adjustment. Perhaps most intriguingly, recent observations suggest these filaments may not be static structures, but dynamic conduits along which galaxies actively migrate and interact, hinting that the universe's large-scale organization may be far more active and evolving than we have traditionally conceived, operating according to principles we have yet to fully comprehend. Imagine the universe not as a random scattering of galaxies floating in empty void, but rather as an intricate, interconnected network of filaments and nodes, a vast three-dimensional web that stretches across billions of light-years, binding together everything we observe in the night sky. This cosmic web, revealed through decades of astronomical surveys and computer simulations, represents one of the most profound discoveries in our understanding of large-scale structure in the universe. Yet it emerges not through direct observation alone, but through the patient mapping of where galaxies actually exist and the mathematical models we construct to explain their distribution. The cosmic web consists of several distinct components: enormous filaments of dark matter along which galaxies cluster like beads on string, vast voids containing relatively few galaxies that dwarf entire galactic superclusters, and dense nodes where multiple filaments intersect, creating the richest concentrations of matter in all existence. When astronomers began mapping the three-dimensional positions of thousands, then millions of galaxies, a pattern gradually emerged that defied the expectations of earlier cosmological models, which had predicted a more uniform distribution, revealing instead this web-like architecture that appears almost organic, almost designed, with a structure reminiscent of neural networks or the internal organization of living tissue itself. The mechanism behind this cosmic architecture traces back to the earliest moments after the Big Bang, when quantum fluctuations in the density of matter were stretched to cosmic scales by inflation, creating slight variations in the universe's composition that gravity then amplified over billions of years, drawing matter toward regions of slightly higher density while simultaneously creating the vast empty voids where matter never accumulated sufficiently to form structures. What persists as genuinely mysterious is not merely the web's existence, which gravitational theory can explain, but rather our inability to fully reconcile its observed properties with our models of dark matter and dark energy, the way it seems almost too organized, too geometrically suggestive of purpose, when we know it emerges from purely physical processes beginning from random quantum fluctuations, reminding us that meaning and pattern can arise naturally from chaos without intention or design, and yet we cannot shake the feeling that something so vast and so intricately structured must contain answers to questions we have not yet learned to ask. Perhaps this is the deeper lesson the cosmic web offers, that we are not merely studying an external structure, but confronting the limits of our own comprehension, discovering that the universe's grandeur lies not in any hidden blueprint, but in the simple fact that complexity, beauty, and order can crystallize from nothing more than time, gravity, and the initial conditions set in motion at creation's dawn. Imagine standing in complete darkness with no artificial light, no stars visible, no moon illuminating the sky, only the profound absence of illumination surrounding you in every direction. Yet beneath this darkness exists a subtle glow that permeates the entire universe, a faint afterglow of the Big Bang itself that has been traveling through the cosmos for nearly 13.8 billion years. Filling every cubic centimeter of space with photons that carry within them the thermal signature of creation itself, a remnant so ancient that it predates all galaxies, all stars, and all the luminous structures we observe today. The cosmic microwave background radiation, discovered by accident in 1964 when researchers detected an unusual noise in their radio antenna that they initially attributed to equipment malfunction, represents the earliest light we can possibly observe. Photons released approximately 380,000 years after the Big Bang, when the universe had cooled sufficiently for atoms to form and light to travel freely for the first time. This background radiation bathes us constantly, passing through our bodies, through buildings, through mountains and oceans, carrying information about the universe's earliest moments encoded in its temperature fluctuations that vary by only 1 part in 100,000 degrees, an almost incomprehensibly uniform distribution despite the universe's ultimate fate of producing countless asymmetrical structures. The human mind struggles to fully conceptualize this phenomenon because it operates outside our everyday sensory experience, existing in a spectrum invisible to our eyes and requiring sophisticated instruments to detect. Yet we have become intellectually comfortable describing it, calculating its properties, and mapping its minute variations across the celestial sphere as though it were merely another measurable phenomenon rather than direct evidence of cosmic origins. We have normalized this astonishing reality through scientific language and mathematical frameworks, transforming the profound mystery of a universe-filling radiation field into an academic subject, a data set to be analyzed, almost rendering invisible the strangeness of the fact that ancient light from before galaxies existed still surrounds us entirely, that we are perpetually immersed in the thermal echo of the universe's violent beginning. Yet when we peer at the precise temperature map of this radiation, detecting regions infinitesimally hotter or cooler than their surroundings, we glimpse the gravitational seeds from which galaxies eventually grew, seeing in these microscopic variations the blueprint of all cosmic structure that would emerge billions of years later, a humbling reminder that the universe's entire visible architecture was already encoded in the quantum fluctuations of the first fraction of a second after existence began. Imagine the universe in its infancy, roughly 380,000 years after the Big Bang, when something profoundly transformative occurs across every corner of existence simultaneously. At this moment, the cosmos transitions from an opaque soup of plasma and free electrons to something fundamentally different, a universe that becomes transparent to light for the very first time. This period, known as the recombination era, represents one of the most critical phase transitions in cosmic history, when electrons finally cool enough to merge with protons and form neutral hydrogen atoms, releasing an enormous flood of photons in the process that streams freely across space without obstruction. Before this moment, the universe was so hot and dense that light could not travel far before being absorbed by free electrons in an endless scattering process, making it completely invisible and impenetrable to observation, much like trying to see through an infinitely thick fog. The photons released during recombination become what we now observe as the cosmic microwave background radiation, the most ancient light we can detect, carrying within its tiny temperature fluctuations the seeds of every galaxy, star, and planet that would eventually form throughout billions of years to come. The mechanism underlying this transformation involves the fundamental physics of plasma behavior and atomic formation. As the universe expands and cools, the thermal energy decreases sufficiently that the electromagnetic force binding electrons to protons overcomes the kinetic energy trying to keep them apart, allowing stable atoms to form and persist rather than immediately ionizing again in the heat. What makes this era particularly fascinating is that we can still detect its direct aftermath through sensitive instruments, observing patterns in that ancient light that reveal the density variations and quantum fluctuations that seeded all cosmic structure. Yet we continue to discover that our models remain incomplete in explaining certain unexpected anomalies and asymmetries within the background radiation's properties that suggest deeper physics still awaits discovery. These anomalies, from unexplained cold spots to unexpected patterns in polarization, hint that recombination itself may have been more complex than our current models suggest, perhaps influenced by exotic particles or fields we have yet to detect, reminding us that even the most thoroughly studied epochs of cosmic history still hold secrets waiting to reshape our understanding of the universe's deepest nature. The study of recombination thus represents far more than historical curiosity. It is a window into the universe's most fundamental laws, where quantum mechanics, relativity, and thermodynamics converge in ways that continue to challenge our best theoretical frameworks and inspire new generations of cosmologists to peer deeper into the cosmic dawn. Imagine standing at the edge of the observable universe, looking backward through 13.8 billion years of time, witnessing the moment when the first stars ignited their nuclear furnaces and pierced through the cosmic darkness for the very first time. This phenomenon, known as the cosmic dawn, represents one of the most profound mysteries in our understanding of the cosmos, for it challenges our fundamental comprehension of how structure could possibly emerge from the nearly uniform density variations that followed the Big Bang itself. During this epoch, roughly 100 to 200 million years after the universe's inception, massive stars formed from clouds of primordial hydrogen and helium, their radiation beginning to ionize the neutral hydrogen that filled the cosmos, creating a period called reionization that fundamentally transformed the universe's transparency and composition. The mechanism underlying this sudden emergence of structure relates to gravitational instability operating on minute quantum fluctuations from the inflationary period, where infinitesimal variations in density grew exponentially over cosmic timescales, eventually collapsing into the first galaxies and their stellar populations. Yet what persists as deeply puzzling is how these first stars could form so rapidly and with such apparent efficiency, considering that current theoretical models struggle to explain the observed abundance and distribution of these earliest objects, suggesting that either our understanding of stellar formation during this epoch remains fundamentally incomplete, or that unknown physical processes operated under conditions radically different from those in the modern universe. We have normalized this ignorance by relegating the cosmic dawn to the category of ongoing astronomical research, rather than confronting it as a genuine conceptual crisis, treating it as merely another frontier awaiting observational data from increasingly sophisticated telescopes, rather than acknowledging that the very laws of physics as we understand them may require substantial revision to account for what actually happened in those first few 100 million years after creation itself. The James Webb Space Telescope has already begun detecting galaxies at redshifts suggesting formation within the first few 100 million years. Yet these observations only deepen the puzzle rather than resolve it, revealing stellar masses and metallicities that appear inconsistent with our models of primordial star formation, and forcing us to confront the possibility that the universe's earliest chapter operates according to principles we have yet to discover or properly formalize. Perhaps most unsettling is the recognition that we may be observing the universe at an age when the very distinction between observation and fundamental theory collapses, where the act of detecting these primordial objects simultaneously reveals the inadequacy of our interpretive frameworks and compels us toward a more profound reconceptualization of cosmic genesis itself. In the first fractions of a second after the Big Bang, the universe existed as an incomprehensibly hot and dense environment where the fundamental forces of nature had not yet separated into the distinct interactions we observe today. And within this primordial furnace, the lightest atomic nuclei were forged through a process so rapid and violent that it determined the elemental composition of virtually all ordinary matter that would ever exist in the cosmos. Big Bang nucleosynthesis represents one of the earliest and most consequential chemical events in universal history, occurring between approximately 100,000 of a second and 3 minutes after the initial singularity, during which time the temperature dropped from billions of degrees Kelvin to merely hundreds of millions, creating a narrow window of conditions where protons and neutrons could combine to form the first stable atomic nuclei without being immediately torn apart by the intense radiation surrounding them. The process began with simple building blocks, primarily neutrons and protons created in equal abundance during the first microseconds of expansion. Yet as the universe cooled to roughly 1 billion degrees, these free neutrons began seeking out protons to form deuterium, the heavy isotope of hydrogen containing 1 proton and 1 neutron, and once deuterium nuclei became stable, they could rapidly absorb additional neutrons and protons to create helium-3, helium-4. and trace amounts of lithium and beryllium before the temperature dropped too far for further nuclear reactions to proceed. The remarkable aspect of this nucleosynthetic process lies in how precisely calibrated it was to the rate of cosmic expansion and the cooling schedule of the early universe. For had the cosmos expanded even slightly faster, neutrons would have remained free and disconnected, producing no nuclei at all, while had it expanded slower, the intense radiation would have broken apart any nuclei formed. Yet instead, this delicate balance created a universe composed of roughly 25% helium by mass and 75% hydrogen, with trace elements comprising the remaining fraction. What makes Big Bang nucleosynthesis so scientifically compelling is that these predicted abundances match extraordinarily well with the observed elemental ratios we measure in the oldest stars, and in the light left over from the Big Bang itself, the cosmic microwave background radiation. Providing independent confirmation of our understanding of the universe's first 3 minutes, and suggesting that our theoretical framework for such extreme conditions contains fundamental truths about reality. Yet despite the elegance and explanatory power of this model, we continue to grapple with questions about why the initial conditions were precisely what they needed to be, why the fundamental constants took their particular values, and how the asymmetry between matter and antimatter emerged from a symmetric initial state, reminding us that even our most successful theories represent merely the first steps toward comprehending the deepest mysteries of existence. Consider the peculiar boundary that defines our cosmic perspective, the observable universe limit, which represents not an actual edge of existence, but rather the furthest distance from which light has had time to reach us since the Big Bang approximately 13.8 billion years ago. This sphere of visibility extends roughly 46 billion light-years in every direction from Earth, a distance so incomprehensibly vast that it encompasses hundreds of billions of galaxies, each containing hundreds of billions of stars, and yet this boundary remains fundamentally incomplete and unknowable because we are examining it from within rather than without. The observable universe limit creates a psychological paradox in human understanding, for it simultaneously represents everything we can ever know while being a direct consequence of our own temporal and spatial position within the cosmos, a boundary that moves outward at the speed of light, yet remains forever inaccessible to us as observers bound by the same physical laws. We have normalized this limitation by converting it into mathematical abstractions and comfortable terminology, speaking of redshifts and light travel time as though they were problems solved rather than acknowledging that they represent fundamental barriers to knowledge itself, boundaries beyond which human understanding ceases, not because phenomena cease to exist, but because causality and light speed itself have conspired to render them forever invisible. This cosmic horizon persists in our collective consciousness not as a source of existential anxiety, but as a useful tool for organizing our observations, a way of transforming the humbling fact of our cosmic insignificance into manageable data sets and observable measurements, allowing us to sleep peacefully under the night sky despite knowing that the vast majority of the universe remains eternally hidden from our view. Separated from us not by distance alone, but by the fundamental structure of spacetime itself. Yet even within this accessible sphere, we encounter further humbling inversions. The most distant galaxies we observe are not as they are now, but as they were billions of years ago, meaning our deepest look outward is simultaneously our furthest look backward. And the light from these ancient sources has been stretched and weakened by cosmic expansion until it arrives at our instruments as a whisper from a universe that no longer exists in that form, reminding us that the observable universe limit is not merely a boundary of space, but a boundary of time itself. Within this temporal boundary, the most ancient light we detect, the cosmic microwave background radiation, originates from merely 380,000 years after the Big Bang, a wall of opacity beyond which no photons can reach us, forcing us to accept that the universe's true beginning remains forever sealed behind this curtain of ionized plasma. A reminder that even our most powerful instruments confront not merely distance, but the absolute limits of what light itself can carry across the eons.